Hello. Good morning, everybody. Yeah, welcome to the stream. How are you? Hello, Sukreta. Welcome to the stream. Nice to have you here. Oh, my mic was enabled as well. I think you like hear double or something. Anyway, it doesn't matter. Yeah, we're gonna just continue. Hey bro, happy to see you stream again. Yeah, it's very cool. It has been like too long since I last did it. I assume you meant the long break I had. And that was way too long. Anyway, I have to go early today, so I'm not gonna stream for that long. I have a meeting at 5 a.m. I think. 5 p.m. is the right thing. 5 p.m. So, actually, I'm just gonna double check that. I think it is 5 p.m. Yeah. Alright, so we're just gonna continue today with the compiler. And I did some work. I didn't do like that much. The only thing I implemented was some kind of assembly function. I just thought I would test and see how it was. This is by no means gonna be like any like finished syntax or anything. This is just me testing, is this gonna work? So it's really cool. You can actually now write assembly functions, and by writing assembly instead of function here, you're basically telling the compiler just to paste this directly in. So I want to, I don't know, I definitely have to compile this if I'm gonna do this kind of thing. So I have to be able to parse this thing. And then the question is, should you have like a unified syntax, or should you just support it like it is? I don't know. Currently it's just pasting in. And the function itself only tells the compiler what to like place on the stack. So it's very cool, this works. let me show you. Thank you for following. Okay, let's do this. Oh, the starting soon is still displaying. There we go. Yeah, thank you very much. 700, yeah, that's right. Uh, 2 seconds. It was actually 15:30, and that is like way too early. So I'm gonna ask for what do you call it, like extending it or something. Yeah. So let's see if this works. It should. Thank you for following. So we can see it prints the. Oops. It prints the tree, which is the syntax tree, in a graphical way, and it annotates it with some types as well. It's very cool. And then it prints, this is cool. So this is not the same, this is my function here. So this is not depending on anything else. If I did this, that will also work, but that's GCC. So then I'm using the GCC printf. So obviously I'm gonna be using this one because now I can get formatting and stuff like that. But it's just cool to see how it works. So the thing I do is that the compiler places this in, I can't remember the register, and it places this in another, and yeah, you just perform some move operations and do the syscall. So it's very simple, and that's for one single char. Or is that for? Okay, yeah, that's one single char. I have to make this function to get a size. So I'm computing the size here, and I'm just calling into the kernel. So that's very cool. I'm very happy with how that looks. So today I want to try to make something more complicated because I think the structures and unions and things are really beginning to come together, I would say. So I want to make something more complicated. I'm gonna actually show you what we're gonna make today. We're gonna make it better, because actually when looking at previous code I've written, it's so bad. Like I don't like it. I'm gonna show you. Let's see, I think it's in Citrus. So this is the operating system we did like last year, I think. Yeah, last year. And this is the main allocator for that operating system. And it's for allocating like small amount of memory. So not like pages or anything. So for pages, I'm using a buddy allocator. So this is a linked list allocator. It is very simple. It does some logic with like combining adjacent blocks when you free stuff. So we're gonna take a look at that. Yeah, so we're basically gonna try to implement this today in the language itself, which is gonna be cool. And additionally, I have added some syntax highlighting here. So now we can actually see, it is easier to see. And the best thing is that I can start commenting here in like gray color. Because without any highlighting, it's very hard to see comments and stuff like that. So it's very cool. The keyboard, I don't have any, I can write what I'm using. I'm using a Digma Race. It is very nice. It's programmable, split keyboard. It's super nice, and I'm using Dvorak. Absolutely recommendable, if you can say that. Yeah, so in order to do this, we have to implement a few things. We need to implement casting. We need to implement I thought about bit operations, but I don't think we need it. But it's very nice to have though. I also thought about implementing like the minus equal, because that is very handy if you're gonna increment something or yeah. So we're gonna try to implement this today, like plus equal and stuff. Oh, we need this one. We need binary like bitwise and bitwise or. And we also need this negation operator. So this is specifically used for aligning the buffer. I'm gonna take in some kind of region, which I'm gonna use for the allocator, and then I need to align both sides. So I need to implement those. And I think I'm using bit operations here. I can't remember where. I think I'm having some high bits, which is telling some kind of like what kind of zone it's allocated from. I don't know. I can't really remember. It doesn't seem like I'm using that. Anyway, it doesn't matter. It doesn't matter. So we're just gonna start implementing that. So I'm gonna delete this. We're not gonna do that today. And I thought about the cast syntax. I don't know what cast syntax we're gonna start with, because I kind of have to determine that now. So in C you normally cast like this. I don't necessarily like it. It is very like, if you're casting multiple times, it's very hard to make, it's very easy to make errors. So I think we're gonna do something like C++. So if I'm not mistaken, C++ does cast, in the wrong keyboard. There we go. I think C++ does this. I think that's also way too explicit. So we might not do that either. We can either do this one. Or this one. Or, I don't know. This also works, I mean. But this is like grouping the arguments a little bit better. So I don't know. What do you think? What kind of syntax should I go for? So let's see if I'm getting a response here. If this is 1, this is 2, this is 3, and this is 4. What should we go for? C++ to me, or old C style. Okay, fair. In the meantime, I'm gonna go in here. 3. Okay. I also like either 3 or 4 the best. I don't know if I like this best or this best. 2 is 2 C++ for me. Yeah. And it's like this weird operator. I was actually planning to use this for something else. So we also need to have like bit operations. And normally, like in for example C, if you have a register and you want to have bit number, for example, 6 down to 3, you would do something like register. Yeah, it would. Okay, so we do like register bit to 3 positions and 1, 3, 4, 5, 6, something like this. So I want to also replace this with some kind of expression here. It doesn't really matter as long as it's like below 8 bytes. And you can, for example, do like bit, and that's going to be a reserved keyword, for example, and 6 down to 0, for example. I don't know. I just thought about it. I feel 3, 4 can lead to mistakes. Number 2 without cast. That's also an option. So like just, and then the parentheses here are optional, I guess. So very like similar to C. It just, like, I like this way better than C because it isn't that confusing. This is something special. So I don't know, really. Should we just go for this one? This kind of cast syntax? I mean, we can change it later. So we could go for that one. I think that will be, yeah, let's go for that one in the start, in the beginning. That's nice. So we need to do, let's just comment it here. We need to add plus equal. Let's not start with that. We're gonna start with casting. Then we're gonna add and or. Let me see, do we have like, this is gonna be a more complex program, so I think we might need to implement this as well. Logical and logical or. We have to do that. I mean, this is simple. It is basically like just if else. So this will be like many if after each other with like a jump at the end. And this will be like nested if statements. So it should be very easy to implement those. I think it's implemented in the syntax though. We can check that. Thank you for following. No, we have not done that. Yeah, summer operators and casting. Let's start with the casting. And bit shift. And probably like bit shift equal. It doesn't really matter. So let's start with the casting. And to be honest, I've looked at a little bit at this like yesterday, and it's very confusing. Like, I absolutely hate how C++ is doing, not C++, x86 is doing this. Like zero extension and sign extension. It is stupid, and I don't really find the correct documentation for this. So I think we're just gonna extend everything to 64-bit, either with a sign or with not a sign, without a sign. All right. So this is bitwise XOR, bitwise and let's add bitwise OR. We could add XOR as well. Exclusive OR. No, we have that one. So this will be just a line. We need logical. I'm gonna take logical up here. Logical and logical OR. Is everything? And plus equal and like plus assign, bit shift assign. And here we have less. So we still need bit shift here. So I'm going to say token shift right, shift left, shift right assign. Dang it, now I have to, yeah, fix those, fix the indentation there. Shift left assign. We need plus assign. Let's take all assigns in one place. So token plus assign, token minus a sign, token division assign. And shift assign. And logical. I think that's it. Yeah, and the casting, for the casting, I'm gonna just use a single, like less and greater. So let's say what this is. Shift left, no, shift right. Division assign equal. I'm never using this like plus assign. I'm using plus assign, but not this. Like very rarely I'm using that. So I don't know. Shift right assign. Shift left assign. I'm never using those. That's for sure. Token logical and. So this will be logical and this will be logical or. The parents can just be a normal parentheses expression to boost this priority, nothing to. Yeah. All right. So we have to make, this is just for printing, I think. I think this is just for printing the operators, the tokens. But we have to add them here, nonetheless. So after not equal, we have right, we have left, we have plus equal, we have minus equal, we have multiplication equal, and we have division equal. And we have shift right equal and shift left equal. So that's those. And then there's a parenthesis there. And then we need to implement these. So after comma, after the comma. There we go. So we have and or. And then we have this one, and just bitwise or. And we have the dollar sign. I don't know why the dollar sign is not there. Probably a mistake. So there we go. More tokens. And you doesn't really, like, you don't really have to do anything else. It's just adding it here, and it will. No, we have to add it in the table as well. What am I thinking? So this and symbol will be used for logical as well. So I'm missing the line. So I'm gonna add a line like or underneath there. So case or. So only one line will be bitwise or. But we have to check for the next one as well. So I'm gonna check if the next character is also a line in which we have two lines, so that will be a logical or, if this is the case. And now we need to skip two characters because we have two characters. Token, and this is token logical, logical or. And we need to do the same thing here. But this is gonna be and there we go. So that's logical OR and bitwise OR and AND. And exclusive OR we have this, we have this, we have. What am I using the dollar for? What am I using the? Oh, I think it's for the assembly function. I'm using the dollar sign for immediate values in assembly, so I have to add it because otherwise I'm gonna have like a non-existing token or something. Probably that should be allowed, but it should be some special token for it. I don't know. We have to add those. Okay, so shift right and shift left. So I'm gonna go up here. So this is shift left, and we have equal. So that is less than. And then we have, if this is open again, that will be shift left. Oh, we have two cases there. So if the next after that again. So I guess next is being set to cursor 1. So I'm gonna read cursor of 2. If that is equal to equal, then this is a bitwise bit shift left assign. So this will be like 3 characters. Token, shift left assign. Two characters, because this is only shift left. X or assign. X or assign, that's good. We don't have that. What is really XOR used for? I'm using it very rarely. It's used for toggling bits, I guess. If you want to toggle something. But I'm never using that. We can add it though, for sure. Thank you for following. Shift left. So is this correct? If next is this, it is either left assign or shift left. That is correct. Okay, so let's do the other case as well. Greater equal. This is going to be right. Thank you for following. Welcome to the stream, Nixie. All right, so I think exclusive or assign. Plus assign. Oh, we have or assign as well. There's really like a few more as well. So we have bitwise and assign, bitwise or assign, and token bitwise XOR assign. So these are very much used, and an or assign is very handy. So this will be that is hard to type on Dvorak. XOR assign. So you need to add the assign case on all of those. So I guess here, else if that. Bitwise and assign. So that is this one. And then we have bitwise or assign. And the final is here. we can just copy it in. Yeah. That seems good. All right. That is everything. So let's see if it still compiles. We haven't done anything too stupid. What is happening? Undefined reference to print. Okay, so this is supposed to be printf. Yeah, okay, cool. This is working. Oh, thank you for the subscription. I didn't see it. I'm very sorry. Thank you very much for subscribing and welcome to the stream. I really appreciate that. Thank you very much. Sometimes it's used for encrypt strings. XOR, yeah, that's right. And for like hash calculations and CRCs and stuff. It's very used, very much used there. A good resource for building a compiler. Yeah, as Nixie was saying. All right. Next thing we're gonna do is, I don't know if we're first gonna start with the casting and then implement this thing, or actually let's implement this, these new operators first, and then we can do the casting at the very end. All right. So the thing with these like plus and assign, these are binary operators. I'm gonna get the C precedence table. So here we have like plus equal. So there is still, because we're gonna reconstruct this one. This is not gonna be like a binary operator. You're not gonna have like, even if you write data plus equal something, this is gonna be constructed as data equals data plus 2, 3, 4. So we have to do this switch here somewhere. I don't know where. We can do it in the parser because we don't need to know any types. This is just like replacement. We have the And what is happening if we do something like this? Then it will evaluate this first, and then it will plus test with that. So that should probably work. I'm not gonna say it's very good to write it like that, but it should probably work. So then we need to change this first, and then we're changing this after. So that will be something like data plus, and you replace this with test plus data. So this node will still be the same. So I'm just trying to think where I'm gonna replace this. Let's go into the parser. I'm using a recursive expression parser, which is a little bit tricky to understand. So I'm just trying to, yeah, here we have it. We can actually do it here. So if we have any like plus assign, we're gonna change it there. Thank you for following. Thank you very much. So the right hand side or the left hand side will be this. So I can probably write it. This will be left plus equal right. Let's move it down here. the binary right we know, and we know the left-hand side. So after this, we can just check if the token is some kind of a sign, and if it is a sign, we make a function which is converting like and a sign to just and then we do the switch here, because the binary node is still going to be the same. So instead of this being a binary like plus a sign, this is going to be a binary just a sign, and then you add another binary operator. So I think we're maybe just going to do it in here. Yeah. Let's try to do that. And we shouldn't have to do anything else. So not in the printer, not in the typer or the generator. This will just work because we're using the same operators as before. So we have to determine if we're getting any like a sign. I'm gonna do just plus, division, multiplication, and minus, because I don't have implemented bit shift yet. A static void, and this is starting with yes, I'm gonna convert. Okay, so let's see. I'm gonna make a function which is converting a token to the right binary thing. So if I'm getting, for example, plus equal, this is gonna return just plus. And if it isn't, it's gonna return 0. And I think 0 is fine because I'm starting at 1. So if I'm getting 0, then it's not one of those. So I just have to find a suitable name for that. I don't know. Yeah, we can say like get get operator assign binary type. It's a little bit long name, but it should be fine. So I'm gonna take in a token here. Or should I take in the so I know the token here. I know the token. So I'm gonna take in a token. We're gonna switch. So you're gonna switch token kind. If we have a token, plus a sign, then we return binary plus. Binary minus, and we also have like return 0 down here. Multiplication assign, multiplication, and division assign, division. So that's only 4. Let's start with just 4. And I think I will have it is that the way I'm doing it? Yeah. That is the way I'm usually doing it. So what we have to do, we have to call this function. And if that function returns something non-zero, so we basically get the transform node kind of this. So binary kind, I'm gonna call it kind for now, is equal to get operator assign binary type, and I'm gonna give it a binary operator. So I'm giving it this one, And if this returns something non-zero, we're going to construct a new node. So we can check if kind. I'm going to call it. We're going to call it. Like, I guess many of these names are just the same. New binary is equal to new binary. This is supposed to take in something. I don't know what. We can do a new expression. I mean, the binary is just 2 pointers, isn't it? It is a kind. I should have an allocate binary. New primary, new binary. It is a new binary. Why the hell doesn't that work? Oh, I'm calling it the same. I'm just gonna call it new though. New then. So this takes in a binary kind, we're gonna give it the kind. So this is constructing a new node, and can we use the same node? No, I don't think we can. So I need to clone this expression. I think I need to clone it, the left-hand side. No, wait a second, is this gonna work? I don't think that's gonna work, because it takes whatever's here, and it copies it over here. So that will be like something like this, and you do this. So now, I don't know. Hello Plexcom, welcome to the stream. Yeah. So we have to do some more checking. We have to check if this is like an left-hand side value, return value. And this is like the first step. So we know the priority. Actually, we can. No. Because we're getting the same thing. I think I'm gonna stop doing it here. Let's take the other things first. I have to think about how I'm gonna implement it. I'm gonna still have it here though. It should probably go in a typer. Yeah, let's implement the rest instead. So this will automatically fix the rest of the expression, assuming I'm adding them here. So I'm gonna add the rest of the priorities here. So case token logical and case logical and logical or bitwise and bitwise or that is those. And we're gonna take those later. We can add a shift right and shift left though. So token All right, so we're gonna add more binary expressions. I don't really know why I have two sets of those. It makes it very convenient. So I'm gonna add more down here. So binary, this will be logical and. Logical or. And binary shift left and shift right. All right. So now it's added there. We're just gonna add it here as well. Logical and. Logical or. Shift left and shift right. Okay, so it's added here. All we have to do is assign some kind of precedence to it in this precedence table. That's the only thing we have to do. So I'm looking at this table, and so shift has like a high priority. We're gonna add shift, we're gonna add those. Okay, so we have assign. This is just assign, that's the lowest one. So this is priority number 1. So I have to give like logical or is the next one. This will be token logical or. So I'm gonna give it 10, which is higher than 1. So I still have something to, like a little buffer. And then we have logical and, logical or, logical and, let's give it 11. And then we have bitwise or, bitwise exclusive or, and bitwise and. So let's give it 12, 13, and 14. That's it. And shift is a little bit higher. So that's above equality. So less equal, plus equal is, plus minus is above that one. So it's right below plus equal, not plus minus. And it doesn't matter. So it's from left to right. So I'm gonna add both here. Okay, so I'm gonna add the same priority on both. Actually, those are gonna go down there. Uh, 23. So that's it. Now everything should be parsed correctly. So we have to add support for them. In the generator. I don't think I need to do anything other than that. In the printer, I think I have some table which is telling what kind of binary operator it is. So we have to add it here as well. So after assign, it is logical and it's logical, no, bitwise and bitwise, oh, it is logical. So I'm gonna do logical here instead. And then it's bitwise and bitwise or, shift left, shift right, and that's it. So this is just for printing. So if I now try to do something, write something in the code to test this, we could, for example, let's define pointer. So let's check if this is aligned with 7, with 8 bytes. So I'm gonna check if, I'm gonna align this with 8 bytes. So I'm gonna check if this and 7, which is 8 minus 1. So this only works for like a multiple, like a power of 2. So it works like 2, 4, 8, and so on, 64. So this will be the 3 lowest bits. That's why it works. So here we do pointer plus 8, and we clear the mask. I don't have that symbol on my keyboard. That is really stupid. I don't have this one. Oh, it isn't there. Where is the not operator? Bitwise not. Bitwise opposite is a unary though. So I need this one. We need to add it in the token list. So I'm gonna add it down here. Token. I'm gonna add it up here. Bitwise not. This is not bit, yeah, this is bitwise not. So I will basically flip every single bit if you use this operator. And that's a unary operator. So that's not gonna go in the binary parser. So bitwise not. That's that. Lexer. Bitwise, I think it's after here. Okay. And I don't have it, so we're gonna make it down here. So bitwise not. That's that one. We have to change the parser to get that one. So we're gonna go down. This is parsing everything, which is top level expression. So what we do for each single thing, we parse the unary expression first, and that will be like the most central unit. So for example, an identifier or function call, it is what's on each side of the binary expression. So on the left and right hand side. Thank you for following. So if we go in here, this is a different function because we need to parse, we need to recurse in a different direction, or the precedence, like it is parsed in the opposite direction. So we're going in here, unary expression. This is called first. So now we check for open parentheses, parenthesized expression, address of. Yeah, so this is a parenthesis expression. And here we have like pointer stuff. So address of and the reference. We're gonna add bitwise not. Okay, so if the token is a bitwise not, we have something like this. So we're gonna make a new unary operator. And we don't have it here, so we're gonna add it in the unary list as well. So unary bitwise not. That's the unary. And each single unary has 3 operators, or 3 things. So the kind is basically telling what unary operator it is. And then we have an operand and a token. So I'm gonna save this. This is the operator. So from this I can get I can get the tilde or something. I don't know what it's called, but not operator. So I'm gonna say the operator is equal to copy token, and we want to copy the current token, which is the bitwise not. And it's also consuming it, so it will have moved as well. It will have moved as well. So we're gonna copy the current token and the operand, which is whatever's after this. So usually I just do this if I don't have anything else. So parse primary and parse suffix. The question is, can you... I think you should do both. We probably can do this. Or parse unary. I'm just gonna call it, we're just gonna recall it recursively. So the operand is gonna be parse unary expression again. And then we return unary. Okay. So this is basically, oh, dang it. Like, I'm gonna use this one instead. So we have like multiplication, and then you have data, or you have data like something like this. So we just say I want the operator here, and then the token pointer is pointing to this opening parenthesis. So basically say I want to parse a unary expression again, and that will parse this one. And if that is a parenthesized expression, it's going to go in here, and then it will jump directly to the suffix expression, because you might still have something here after that. Anyway, I think this should work. That is bitwise not. So in the tree printer, we're going to add it here. Bitwise not. All right, so let's test and see if this works. So I want to align the variable pointer with 8 bytes. So I'm gonna say pointer plus 8. And I'm gonna have to add this to the keyboard. Luckily I don't need it that many times. And 7. So this will say like pointer is some binary number, right? And then 7 will be these 3 bits here. So basically test to see if any of these bits here are being set. So if any of these bits in the pointer is being set, then it's not aligned. And if it's not aligned, you increase the entire thing by 8, which will increase this number, but we'll still have the same thing here. So you make it bigger, and then you clear this mask. So you want to clear these 3 bits. So then you're saying and this bitwise not 7. So the bitwise not will basically flip every single bit. So we do this instead. And if you do this one and this one, then it will be unchanged here, because this is 1. and those 3 bits will be 0, because anything and 0 will be 0. So that's how it works. And obviously it only works for power of 2. So it's nifty. Do you use any code formatting plugin? No. I don't know. No, this is just a language extension. It is very simple, like 60 lines. I just wanted to highlight the keywords and the comments, and oh, I spent so long time yesterday figuring that out. At least 1 hour. At least 1 hour. Like regex, and oh, it's so annoying. And it's badly documented as well. Or it's hard to find it. Let's see if this works. So the typing is failing. And by the way, the typing is failing. I'm gonna fix that right away before I forget it. Yeah. So the typer I'm giving it a typer. This was, I don't know if you remember, but the last stream, sometimes we had problems with the typers sometimes failing, and it is very strange. And if a program sometimes fail, it is likely because of some uninitialized variable, because it's on the stack and what's there can change. So that was actually just a typer not being initialized. So let's add a new function for allocating a typer. So I'm going to take like new typer. I'm going to use calloc. So size of typer, and so now it's 0 initialized. Yeah, we'll kind of have to do it here as well. It doesn't make sense to say type resolved and unresolved types. Current scope is 0, current struct is 0, so I'm just going to return it here. But it has to be 0 initialized. So return typer. So when I call this function here in main, I'm basically allocating an object here, and that's not very good. So I'm gonna say typer so it's equal to new typer, and then we're gonna give it just a typer. So that should initialize everything. That isn't the reason why it failed, but it is nice to have anyway. That's typer. So we have to set the type resolved to true. We don't necessarily have to do that because we're setting it to false here. So me setting this to true is just for entering this loop. So by changing this to a do while instead, I think I can eliminate the need for doing that. So I'm gonna replace this with a do while instead, which we're also probably gonna support in our language. So passes plus plus. So we're going to do this while unresolved types and type resolved. I'm going to change these names, but it's fine per now. And we're setting it to false in the beginning, and then we're trying to type the code units. All right, let's see if we're getting it correctly. So we have an if. So now we have a condition which is binary and, bitwise and, that's working. Compound expression binary equal, so pointer and and we have a unary bitwise not. So bitwise not 7. Yeah, so let's implement those. Let's do like an logical and a logical OR as well. So I'm gonna say if 45 and 0 do something, and if 45 or 0 do something. Condition binary and logical OR. So that's working. Thank you for following. Like, what is that? K Karki or something. Thank you for following. Tilde is correct. Okay, nice. No, this is like a programmable keyboard. I have to manually set every single key because I've changed so much. Especially considering the Lexron parse is just declared just above it. Yeah. Let's go in the generator and generate code for this. So I'm gonna start with binary, like bitwise and. I believe the instruction for that is and. It is in ARM. And instruction. Let's do bitwise and. Bitwise or. It is and or. Let's do bitwise not as well. I guess it's the same thing that the return value is on the right hand side. So it's just not. Performs a bitwise not operation. Okay. Let's go a little bit more down so we can see where it starts. So when I'm generating a function, I'm starting basically here. And I'm generating some like starting, this is a function kind of thing. And I'm computing the local variable offset, which is setting up the stack frame. And then I load the registers. So if this function is going to be called with some arguments, I'm loading those. And then I'm generating the body basically, which is in here. And the first time this is being called is a compound statement. So the compound statement is gonna just generate statements. So in our case, we have an expression statement, which is here, and we have a binary expression statement. So this is supposed to happen. And yeah, so we're gonna go down here, binary plus, minus, and so on. And we're gonna do cases for binary bitwise and binary bitwise XOR and binary bitwise not. I didn't try XOR, but I guess it works. Yeah, that's good. Let's start with a binary and. So I guess I'm saying it up here, but this is being set up like this. So the left-hand side is in RAX, and the right-hand side is in RDI. I don't know what this is like this. So basically, in any binary expression, you're gonna store the result in RAX. So at any time, any expression is gonna be stored in RAX. So that's why that is on the right-hand side. So I guess we just do emit like this. We're gonna add RDI and RAX, and you're gonna store the result in RAX. And this is OR. And this is XOR, and this is not. I'm guessing this is gonna be XOR. Have to check. Oh, it's XOR. Okay. So just by doing this, I think this is going to be implemented correctly. So we can see if we can align a number. So let's don't do this. I have a pointer. I'm going to say like, I'm going to give it 17. And I'm going to print a number. Pointer. So now I'm aligning it with 7. So this is going to align. This is going to align up. And then I'm going to take the align down case. So we have like a new pointer is equal to 17. And this is going to be aligned down instead. I guess it's just like this. All right, so the first should align up and the last should align down. Binary bitwise XOR. We don't have binary bitwise XOR. So we have to add this here as well. So if we have a token bitwise XOR, we're going to return a binary bitwise XOR. And we're going to add it here as well. So let's see where the XOR is coming in here. Binary XOR is, do we have it here? Token bitwise XOR. Okay, so this is just using the token, so that's fine. Bitwise not. And that is not a bitwise operator, that's a unary operator. I have to fix that. Next project, writing an OS in my language. Yeah, definitely. That's gonna be the next project. I mean, today we're gonna, I don't know if probably there's a few people in the beginning and more people in the end. So I was saying that we're gonna try to make an allocator today. We're basically gonna remake this. So the linked list allocator from my previous OS. So it should be able to do pretty much like a lot of things, which is very cool. We have to do casting first, because one of the things we have to do here, we need to cast some specific address to some kind of structure, because we're gonna, like, we're given a pointer. So let's say you call free, you're having some memory and you call free on that memory. So you're gonna give the function a pointer, and the pointer, the function is gonna take, it's gonna subtract some bytes from that pointer, and it's gonna cast that to a structure. So basically it's expecting a structure before the pointer, and that's gonna tell something about how it's allocated. There's a language that's special, it's called luxury. Yeah. How long have you been working on this language? Like, this is the 5th day. I did a little bit yesterday, but this was just like testing, trying to fix the errors. Eventually coming and just noticing that I didn't initialize the typer. That was the only thing, and I did what you call the syntax highlighting. So this is gonna be the 5th day. It's like 5 days with 8 hours. But I have done it before, that should be said. So if you don't know how to do this, it's very hard in the beginning, I would say. But once you know how you should do it, it's very simple. Yeah. All right, bitwise not is not a binary operator at all. So this doesn't really make sense, because this isn't anything. So I'm gonna save this instead. And this doesn't make sense either. So you're gonna instead go in the unary expression, and I'm gonna make a case here. So unary kind, bitwise not. So we have to remember, like, I'm using the wrong thing. Let's get the operator. I'm just gonna say like not. So we have not, and then we have some kind of expression, for example, data plus anything. So what this unary operator, like this unary structure, is telling us, it is telling us what this is pointing to. So first we have to generate the expression for whatever this is pointing to, and then we can generate the not instruction. So first I'm gonna generate the expression, which is the unary operand, and then we do emit not RDI, and this is of course going to be RAX. Thank you for following, Nimbus. So this is returning the result into RAX, and then we're just nothing RAX, and that's it. So now it should work. So typer starting. Typer failed. Why the hell does typer fail? This isn't looking good. New pointer is 17. Let's try to make a type of this. Is this in the unary? This is a new unary operator. We might have to type this. I guess maybe it doesn't find the type for 7, because this is a unary. I think that's the thing which is failing. So even here it fails. So type result type, find strict offset, line result unknown, statement, type unary expression. So here we have added a new case where we say unary bitwise not. So in this case, we're gonna type this. We're still typing the expression. The problem is we're not setting the type. We're typing, so when I do type expression, this will basically assign a type to this expression. And as you probably see, I'm not assigning the expression here. So this expression, like the unary expression, doesn't have a type. So in case this is a bitwise not, this will have the same type, I guess. So I'm just gonna set the expression type equal unary operand type. There we go. Number of operators, mismatch for nuts. How do you do not correctly? That is a good question. Where did I have it? Oh, there we go. Okay, so it's basically just one operand there. So we have to fix this. It is just supposed to be this. Oops. And there it works. So you can see, even though I'm giving 17, I'm first aligning up, and then I'm aligning down to 8. I could also say like 16 here. Let's do 16. So that's cool. It's gonna be like 16 and 32. So that's very nice. We're gonna use this for aligning the pointers. So first step is done. We need bit shift. And we need this crappy thing. I'm gonna take this at the very end. We don't really need it in the beginning. You can use it. Oh yeah. Hello Addo Haney. Welcome to the stream. Yeah, so it takes just one input. So if the expression results in a boolean 0 or 1, it will just flip the condition. Yeah, that's correct. And that's really cool. I've seen it sometimes like this. What is this doing again? I don't know, there were some cool use for it in C. I'm not gonna say cool, but it is like a nifty reason for doing this. It is converting something, I can't remember. Anyway, let's do logical and logical OR. Okay, so we have done this. XOR, we can test XOR later. We need to implement those. So those are going to be a little bit different, I think. Because you can have like an arbitrarily many expressions like this. So I'm going to make a test for it first. I'm going to say, I'm just going to use numbers. So this should be 0. So therefore I'm going to say like fail. And then let's do OR as well. All right, so we're going to implement those. So this is parsed like we have one binary node, which is a logical and the left hand side will be this number and the right hand side will be this number. So basically we're gonna assume this is only one single number, and we're gonna just construct in case of this. We're gonna think like that, and then we're just gonna recurse. So it should be fine. I'm gonna bring it over here instead. So this is a binary operator. So binary, logical and. Okay, so we're gonna take this first. Are you planning on dealing with null reference exception at compile time? No, I'm not gonna do that. I'm gonna implement a different kind of thing. We're gonna do that today, actually, because it's very nifty. Because we're gonna eventually make some kind of like alloc function, and this will return a. First of all, it will return a void pointer, which I'm gonna write at just like the pointer symbol. I'm not gonna have any void specifier. I'm just gonna say like it's returning a pointer. I also wanna have a question mark for maybe this is a pointer. Maybe it's valid. So basically a question mark is just a pointer, and I guess when checking the value, it changes type to a pointer. So if you do some kind of if, let's take in some data instead. That is very nice. Like I would say 90% of my mistakes in C is just because I'm dereferencing something 0. I'm not checking that. So if I have like a pointer to some kind of token, I have to check data. If data is equal to 0, then after this, then this sign will switch to a, it will switch to a normal pointer. So if it's in here, then this will still be not a valid thing. So I have to deal with detecting this kind of condition and propagating that. I don't know how to do that. We have to think about it. But I will implement something like this. Yeah. Option. Rust deals with that. Yeah, I've taken a look at the option thing. Maybe I just didn't understand it correctly. I don't know. Okay, let's take this first. This one and 21. So first we're going to generate the first expression, and we have to compare it against 0 because we're going to check if this is true. If it is 0, then we're going to jump down here. So this I'm going to call like if end. So if this is 0, then we're going to jump here, because since this is and, we have to all have to be satisfied to go here. Yeah, so it has to go down here. Otherwise, we check the next one. And this is also going to evaluate to some kind of thing, if I'm remembering correctly. I think this is going to evaluate to either 0 or 1. So depending on what this is, I mean, if this is 0, then we don't need to do anything. But if this is true, we're gonna move 1 to RAX. Something like that. So we need to generate the expression for this first. Which we are doing, in fact. I think we're doing it up here. Oh, that's gonna be wrong. That's gonna be very wrong. Okay, so I think I have to do it like the assign case, because I need to manually generate these instructions. So if binary kind is equal to binary logical and, okay, let's take and first. We're gonna generate expression for the left-hand side, which will be this number here. So this will effectively place that expression inside RAX. And then we need labels there. we need labels. So we need the same thing as I'm doing. We need the same thing as down here. So what I'm doing, I'm having a static variable and I'm just incrementing the counter. So let's make a static u32. I'm gonna say and counter is equal to 0. And perhaps since I'm gonna recurse, I need to save this variable. So I'm gonna make a number. Plus plus. So this is a unique number. The reason I have to do this is because I'm gonna recurse in here. So this might also change the same thing again. That was pointed out the previous stream, I think. Go with static libraries. If the compiler can catch 99% of them, but not some edge cases, it's good enough. Yeah, for me as well. All right, so generating for the left-hand side, we're gonna emit compare with 0. So compare 0 with RAX. And if this is true, so jump equal or not equal. If this is false, if this is true, so I'm gonna say jump equal. If this is true, then this number is 0. So this entire thing will fail. So Rx is containing the value 0. So I'm gonna jump to and give a number as well. And I'm gonna make a label down here, which is called and number. So this will jump down here and it will hold 0 in the register. So that's also like, if I don't necessarily use it all the time. I'm beginning to use it lately, but if this is failing, it will only check the expression. Like it will check this one, and if this is failing, it's not going to check this one. So let's say you have a pointer which is valid if you have something else satisfied. You can check if this is satisfied here, and then you can assume that pointer is valid here. I'm doing that a few places. Okay. So jump end. Okay, so I'm gonna generate the next hand side. So generate expression binary rights. I'm gonna in fact do the same thing. Compare with 0 and jump. And this will recurse. This will take to rest. This is also going to jump to the end, because we need to jump. If this is not the case, we need to move 1 into the register. So I'm going to say move 1 into racks, and that's it. So jump to the end there, and okay. Let's split it up, it's easier to read. Is this correct? I think that is correct. And we need to implement this, logical OR. So that will be true if either one of these, like at least one has to be true. And if one is true, we're gonna skip checking the other ones. So this will also do the same thing. Static u32 or counter equals 0. Thank you for following. Okay, so we're generating the number. We need to compare the first expression against 0. So generate expression. We're gonna do this. Okay, so jump equal. Yeah, so this is wrong, in fact. So if this is 0, you know this is never going to be true. So therefore you jump to the end. If this is 0, you still have to check the rest. So it's like opposite. So if this is non-zero, then you know this is going to be true. So here you check for 0, here you check for non-zero. So I'm gonna say jump if not equal. So if this is not true, this is some kind of value, we say or end. And we have the label here, so or end. So that will just contain this value in the register and it jumps here. Oops. Which is wrong, because now RAX is containing this value here. Is containing that value. So we have to move one to the register. I'm gonna call it or1 instead. So this is gonna set the number to 1. Yeah, so that's a label. So this will move 1 into RAX. That makes sense. So we're gonna jump to or1. And if nothing here is true, we're gonna jump past this one because it's gonna be 0. So that will be explicit because we have something which is still 0. So this will automatically jump past this stage. So just a regular jump. I'm gonna call it or end. Okay. So this is setting RAX to 0 to 1, and this is end. So unless I'm actually jumping here, I'm never gonna set it to 0. I'm never gonna set it to 1. So I can jump here to 1. Okay, fair enough. Generate expression, binary rights. Thank you for following. Welcome to the stream. Binary rights. And I guess it's the same thing here as well. So compared to 0, jump if not equal to 1. Generator to 60. Assertion failed. Did we have a return statements there? No. That's it. No such we're missing colons here. So all labels have to have colons. No such instruction branch. Jump not. Isn't it? Is it NE probably? I think it might be NE. I have it down here. Jump equal. not using anything with not equal. Oops. It seems to be just jump not equal. Yeah, it's any. So jump not equal. There we go. Fail, success. Shouldn't both succeed? This is true. In fact, I'm just gonna print success if it goes in there. Like, I'm gonna print an OK, OK1, and an OK2 here. I'm gonna disable these else statements. So if this is true, this is supposed to be true. So we should get OK1. And this is also true because you're doing OR. So let's say all of these as being 0. Let's set this to 0 as well, so we can use it there. So now we have only OK1. And as long as I set this to something which is not 0, okay, perfect. If I set this to 0, then I'm having only 2. So I guess this is working. We have to check if it returns the right value though. Having bool. I added the syntax highlighting for bool even though I don't support it yet. We're gonna add support for it though. So I'm gonna say b is equal to pointer and 0. Let's do 2, 3, 4. And I'm gonna print b. So this should be 1. B is equal to 1. So even though I'm having like expressions here, it is still 1. If this was 0, then I should have 0, which is correct. Oh, this is so cool. Very nice. So I assume it's the same here. We can probably test it. So I'm using OR instead. So this will be true. So now it should be 1. And it is 1. Perfect. So now we're a bit closer to our allocator. So we have done this. Bit shift. Let's do shift as well. What is the difference between arithmetic and logical? I don't know. I'm gonna do it later. Doesn't matter. I'm not gonna. I thought I would need it. In fact, I don't use it in the allocator, so I'm gonna do it later. We're gonna do the casting first. Yeah, so let's do the casting. So we will have something like I want to cast data to a U32 and store it in here. I'm not sure if I like this casting. I'm not sure. So let's say you have like multiple, you're gonna cast this as well. So you want to have like, and this is gonna be, wait a second, this is gonna be, you can have something like this and plus some value. For example, you would cast it to a pointer. I'm pretty sure I'm gonna do that. So you take some kind of pointer and you're casting it to a value because you want to increase it by this many bytes. Or it makes sense for me to write the type first because you know what you're gonna cast to. So I want to eventually cast to a pointer to U32, and what I'm gonna cast is a U32, which is data plus 345. So there's more to write. The question is this better to read? Or this? I don't know, to be honest. I don't know. I feel like there has to be a better way as well. Yeah, that's the C++ way. I don't know if I like that. I mean, this is very clean. And probably you shouldn't be doing this because it's hard to read. Like for the parser, it doesn't matter. It really doesn't matter. It is just for the reader, like what makes sense to read. And I mean, if I would write this, if I would write something like this, you have a pointer, right? You have something which is a pointer to U32. Let's say it's a value. So you want to increment this by 4 bytes. I don't know how I would do that, to be honest. You can't say address is equal to cast test to a U64. And then you say test is equal to address plus 4 casted to a U32 pointer. I don't know, to be honest. I think I'm just gonna go with this implementation there. Hello, Trello Woods. Welcome to the stream. Hello. Okay, we're gonna go with this one. We might change it later though. And this is a unary expression. So this will be interpreted as the same as like a normal identifier. So here we need to have a new node because we need to store the type as well as the expression, and we don't have that currently. So we're gonna have a new cast node. Which is an expression. So I think I will add it here or in the unary. Unary kind. No, I'm gonna add it in the expression here instead. So we have a cast. Okay, cast. So we need to know, we probably need to have some kind of token. So I think I'm gonna store, since we're using explicit cast with a keyword cast, I think I'm gonna store this token here. So I'm gonna say cast token It will basically point here. And then we have a type, which is cast2. And we have an expression as well. I don't think we need anything more than this. Cast an expression. That's fine. And the cast is in here. So this expression kind of needs to support cast as well. So I need to make a new expression for the cast. All right. Let's add it in the parser. This is in fact a primary expression, so it depends how we're gonna interpret it. If I say cast data to U32, should it be able to do dereference it? Yep, yeah, definitely. You should be able to do this. And you should also be able to do this. If you're casting to a function or something, if you're casting to an array, you probably should be able to do that. So this is going to be a primary expression then. Yeah, so it's going to be in here. So this is returning a new expression. Suffix. I'm gonna try to write it in here and just see how the tree looks. The token is still gonna be the same. Here I'm actually making a primary. I'm assuming this is a primary. So a primary might also be just an expression. I'm gonna add an if here. So I'm gonna compare this token against the keyword cast. What you're gonna make if it's not made. So keyword casts. We're gonna add it up here as well. So this is what it's using for actually comparing. So this is what I'm actually gonna have in the code. So now we should be able to recognize cast. If this is a cast, we do expression. Okay, so we're allocating a new cast expression. Why doesn't that work? Oh, probably like this. Huh. Oh, there we go. Expression kind. Expression kind, expression cast. That is defined. I'm having it wrong. Struct cast. I don't know why it doesn't autocomplete. Oh, I'm having this. That's why. There we go. So cast2, we can start with a token. So I'm gonna copy the cast token, which is here. And I'm consuming, so it's already pointing to the next one. Well, I can write the cast syntax here. Let's write it here. So this is the syntax, not the semicolon, just this. Which means after I'm copying this token, like if I'm going in here, I'm pointing to the opening parentheses. So I'm gonna skip the token. Close parentheses. So now I'm skipping this one, and now I need to parse the expression, skip a comma, and parse the type. That should be very simple to do. Welcome to the stream, Eru. Thank you for following. So cast expression is equal to parse parse expression, parser, init priority. This is just -1. That's for, never mind. And then we have cast2. We're gonna expect a comma before it. Thank you for following. Welcome to the stream. Thank you very much. Parse type, I guess. And this will actually force a type. Yeah. So this is a new cast, and this will actually be the primary expression. I'm just going to return return the cast. So we're copying the token, you're parsing the expression, and cast2. All right, that should work. It's a little bit like annoying to have it here, but I guess it's fine. It is a primary expression, so it is between the postfix and suffix. No, the prefix and postfix. All right, we have to go into the printer to support printing cast expressions. So expression cast. So we have a cast expression. I'm gonna first obtain it. And then we're gonna do indented print. So I indented print, that's basically doing this. It's printing what I've marked now. That's the indentation. And then whatever I write here is gonna come after. So I want to say cast, and I want to indent this. So I want to have something like cast, and I want to paint this line, and I want to say the type, and so it will be the type after here, whatever, and I will paint this one as well, and then I will have the expression, which is coming after this, and here I don't want to do anything like paint this one. So first I'm going to store, and the indentation, like when I'm marking stuff to be printed. 2 seconds. Yeah, okay. When I'm marking stuff to be printed, I'm basically so this current indentation, when I'm printing cast, I'm going to use the same indentation as this. So if I'm saving the indentation now and marking that as to be painted, that will be directly beneath cast. So it will be that indentation level. This will be like cast indent is equal to indentation ++. And then we're going to mask the cast indentation to be true, and to be false. And here we're gonna do indentation ++. Or we're doing it here. So not. We're gonna do it down here instead. Indented print type. And then we print the type. And print all. This is just telling if we're gonna print like a short version of the type or the entire thing. Because if you're using structures, then one single structure can easily be like this big. And if you have like 10 expressions which is all having this type, it's gonna be very, very big. So that's sort of what this is for. So print all, I'm gonna mark it as true. It might be nice. We can mark it as false if we need it. And then we have our indented print. Actually, I'm gonna indent this further. Okay, so this is a type. You're printing type, you're indenting before the print. And then I guess you're printing the expression. I don't know if you're gonna need to do that. Let's just print the expression after. So that will be cast expression. And then you do minus there. That should be fine. And a break. So let's see if that does it. Print type true. This is supposed to be cast 2. Oops. It's parsing. So now I just have to test this and see if this works. At least the parsing phase. Let's have it to like. So what I'm gonna cast is a new cast. I'm gonna cast data. Well, let's do argument. Argument count is gonna be casted to a pointer to an array of 34 U32, and that's gonna be casted to a U64. I don't know what that makes sense, but that's this. Let's take like plus 234. So that's interesting. We're getting something. We're getting a cast. So it's basically casting 2. I don't want to have type there. I want to have cast 2 because that's more expressive. So binary cast is going to cast to a pointer to an array of 34 unsigned 4 bytes, which is the argument count. And then this cast expression is being added to 234. And then this is casted to unsigned 8 bytes, which is up here. So the parser is working. So we just have to implement this. Any plans on packet manager? To be honest, I don't know what the packet manager is. I never used that before. What do you mean with packet manager? Do you think libraries or I don't know. Libraries? I haven't thought about libraries. I don't know. I kind of don't want to have anything like any libraries. It is just going to be like GitHub repos. I don't know. I have to think about it. I think it's going to be just source code on GitHub and just pull whatever you need. It's going to be like some kind of fancy way to do that though. I don't know. I think cast U32 data is the more clean added to above. Oh, that was the old one. Yeah. Is this some kind of recursive descent parser? Yeah, it is. It's very, very, very cool. Like, this is on my GitHub, by the way, if you want to take a look. And the entire thing, which is parsing literally every expression, any expression, is just here. Oh, it's down here as well. It is not that much. And the priority thing and the binary thing, that's only this function here. So if we're not gonna have like postfix and suffix operators, no, prefix and suffix operators, it is in fact very, very simple. It is just that this is a little bit tricky to understand. You basically, that's the initial priority. You give it a priority which is lower than anything you're gonna possibly get, so that if you have the same priority, it's just gonna loop. You're not gonna exit this loop until you're getting 0, because this is not valid. You have some kind of operator which is not an operator. So that's what's terminating in most cases. This is terminating in all cases. It's this one. So basically check if the priority rises. And if it rises, you continue to recurse. That's the thing. It's very smart. It is, really. Anyway. It's an easy and convenient way to grab external libraries. Okay, so we're going to implement cast. And the thing about cast, we can cast to whatever we want. I'm going to implement that. The typer certainly need to do something. Because I'm not typing anything in the parser. I'm first parsing it, and you can see I have the typer failed. Okay. So typically I'm first parsing it, and then the typer is filling in some stuff. So that's why I'm printing it 2 times. So we need to handle the cast expression in the typer. And I guess that's just adding a type. We should know the type, so we should just add it. Just have to think if the structure is going to work. I think the structures will work, because in the very end we're just having like if I'm writing, let's do like dot token dot one dot test or something. It basically starts with this one. So this is a dot expression. It will first recurse down here, and then it will find this one. And I think I'm generating definitely the address of this one. I'm just, how do I find these offsets? This is really hard to actually understand. It did make sense a few days ago. Okay, so if this is a dot, we're generating the address first, and then we do expression.offset, which basically means that every single dot has an offset. So that I'm fixing in the typer. So the typer is going to go over and find all the offsets. And where am I doing that? Expression statement, type expression, dot expression. So this is the dot. I just want to know if I'm using the type or if I'm using anything else, because I only want to use a type. So I'm using the expression type. Okay, so if the expression has a type, and while this is a pointer, while dot expression type is a pointer. Yeah, okay, so here I'm basically fixing, in C you typically have to do this if token is a pointer, and you do this if token is not a pointer. So I'm doing only dot. So I have to convert this one to, I'm converting this one to this, I think. That makes sense. So you're first referencing this, and this while loop is basically converting this to this. The thing is that this might also be a double pointer. So if you have something like data, which is a triple pointer to a token, in C there is no operator for doing that. So you have to do like 2 times data, and then you can use the arrow. So this while loop is basically for fixing all these. So if it's 3, it's fine. It's just gonna generate 3 dereferences first. And I guess that's just depending on the type. So that should be fine. And then it's the interesting part. So then we have to look up the member in the structure. And the dot member name is still the same. This is fine. And then we look it up in the dot expression type. So the only thing we have to make sure is fine is the dot expression type. So basically when I'm casting, if I'm casting something to a structure, then I have to give that, then it's fine. I'm just gonna copy the type. That should be fine. That should do it. All right. So I have to make sure the actual expression of the cast, the actual type of the cast expression is correct. If that is correct, struct member will still work, and everything else as well. Okay. So we have to do conversion between numbers as well. So we're gonna cast to like a U32 and U8. I have looked at it. It doesn't make any sense. So this might be very wrong, and please let me know if I'm doing something really stupid. But basically you want to convert between any predefined types, any basic types. I'm gonna show you what the basic types are. So the basic types are these. So like U64, U32, you're gonna convert between any of those. So from any of them to any of them. That makes sense. Like that should be doable. So you can either like have statements for checking each single combination. It's going to be like 4 times 4. No, it's going to be 8 times 8 combinations. So 64 combinations. Isn't that true? 64, maybe a little bit less. I can't remember my statistics. It's going to be a lot of different combinations. And since this is just converting from and to, it's very convenient to use an array of this, like a double two-dimensional array. Yeah, so 2-dimensional array, and each single entry is going to just have the instruction, which I'm going to use for converting. And we probably should take a look at the conversion. x64, I think it's basically like flavors of the move instruction. So move byte to quad sign extend. Yeah, so S. To be honest, I don't know why I have to specify move quad move whatever. You have to actually specify if we're going to move a byte. It is not just enough to use the register name. I don't know why. Move 0 LQ. assign LQ. Yeah, like you have basically two different things you're gonna do. Either you're gonna sign extend or you're gonna not sign extend. So if you're gonna cast upwards, I'm gonna actually show you. And I'm not an expert in this. Yeah, we can start implementing this right now. So generator. Oh, we are in the generator. So I'm gonna, thank you for following, welcome to the stream. Generate binary. So this is just a normal expression. So generate the expression, I'm gonna make a cast expression here. And then we're gonna make the table up top here. Okay, so if we have an expression oops. If we have an expression cast, we're gonna call this function. And we're gonna obtain the actual cast object first. And cast2 and cast token and expression. Whatever. Okay, let's implement the table first. So this is going to be a static const chart pointer, and then we have a double array. So I have 1, 2, 3, 4, 5, 6, 7, 8 different options. So I'm going to make a table of 8 times 8. And then I have to say like, this is the first entry, so that will be like, oh crap, what is this? It is so hard because it's written the wrong direction. I guess this is an array of, like this is the byte index. So this, like the index here, will refer to the width of each single element here. So the first one, which is 8, will determine how many of these I'm gonna have. So I'm gonna have like 8. Then I'm gonna have some instructions here. I'm gonna mark them as instructions before. So let's use just the extension. Yeah, so I'm gonna say like SLQ. So it's gonna transform a long to a quad, which is casting a U32 to a U64 with a 0 extension. Oops. And then I have it aligned neatly. 1, 2, 3, 4, 5, 6, 7. And 8. All right, so that's 1. One, 2, 3, 4, 5, 6, 7, 8. All right. So let's start with 8 bits. Now this is very inconvenient. I'm actually gonna give it some more space here. There we go. So I'm gonna say like U8. Let's start with S8. And U8. And then we take S16, U16, S32, U32, S64, U64. U64. There we go. So I'm going to cast from this to this, written in the direction you read. Yeah, I can go up here. So U8. No, S8 first. Thank you for following. S64 and U64. So this is gonna have like the index number 0. So 0, 1, 2, 3, 4, and so on. So like eventually I'm gonna have one single instruction which is gonna do the casting for us. So one single instruction for doing that. So we have to implement all those different things. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. So this is, let's just use this. So it's different between like sign extension and 0 extension. So typically I'm gonna write one example first. So I'm gonna call this, it CLQ. CLQ. That's actually gonna be SSQ. I can just use CLQ. It's like a weird instruction. It's basically just a move. So I'm moving EX to RAX. The thing is that when you move anything, if you move a 32-bit value to a 64-bit value, you automatically clear the high 32 bits. So those bits are going to be 0. So if you want to 0 extend a long to a quad, you just do this move. So that was a bad example. So let's use SLQ. This is going to sign extend. And there is like a instruction for it. So it's deprecated that you're supposed to use move SXT instead. I think you can use it in AT&T. I don't know. Move SXT. Thank you for following. Welcome to the stream. And racks. So basically, you're gonna move. That's also a bad example because I'm not using. Basically, you're gonna move a long to a quad. So a long. You have byte, which is 8 bits. You have word, which is 16 bits. You have long, which is 32, and you have Q, which is 64. So we have to keep those in mind. So if you want to do, let's say you have something here, some value here. Now I'm getting unsure. How does this actually work? Yes, a sign bit here. So I should probably have looked up this before stream. I think I know like ish how 2's complement and negative numbers work. So you probably should arrest me if I'm saying anything wrong. But if this is a positive number, then this bit here will be 0. And if this is a negative number, then this will be 0. Like, let's say this is 45. So if I'm interpreting this as a positive number or a negative number, it's going to be the same. Exactly the same. But if this is a signed 8-bit number, then the top bit is telling if this is a negative or a positive number. So if this top bit is 1, then it will be minus 45. Or it will be like 200 and no, 140 something if it's unsigned. So when interpreting this as a signed number, you're basically looking at this bit here. The thing is that if you want to extend that one, so this is supposed to be minus 45, right? If you want to read this entire 16-bit value, so you're going to cast a signed 8-bit to a signed 16-bit. Basically, you want to read a 16-bit value and get the same number. If you're reading this one now, it's going to give you a wrong result because the top bit is 0, so it's going to be a positive number. That's the problem. So in case you want this to be a negative number still, you would have to sign extend, and that's the thing with the S here. So when I'm doing S, it's going to be the same as the actual instruction. I'm gonna take whatever this bit here is, I'm gonna propagate it up here. So if I now read this, it looks very weird, but when taking the 2's complement, it's the same. So this will be minus 45 still. It doesn't matter how many ones you add, it will still be the same number. I hope that makes sense. So let's take another example. If I'm going to assume that everything here is non-valid, except the one the type I'm actually having. So if I'm having a U8, I'm going to assume that everything here is not valid. So if I want to cast a U8 to a U64, so I want to do U8 to U64. -1 is FFF in U32. Yeah, that's correct. -1. So I think you basically take you take the positive number, which is 1, you want -1, and then you flip every single bit, so that's going to give you this, and then you add 1. That's the 2's complement. That's going to give you FF, or 8 Fs if it's a 32-bit number. So if I want to convert from U8 to U64, I'm going to use an instruction which uses only the low byte here. So I'm going to grab the low byte, and I'm going to move this into the entire register, and I want to 0 extend. So I want to clear all these bits. If I would interpret this as a signed number, if I want, for example, signed 8 to 64, I would have to sign extend up here. So that's the deal. That's the thing to remember. So I'm doing long to quad first. Quad to quad doesn't really matter. If you have a 64-bit value, it's a 64-bit value. So I'm gonna say 0 word quad. And sign extend word quad, 0 byte quad, and sign extend byte quad. So it's going to be move 0 word quad. So I want to move AX to RAX. And SWQ RAX. So this is going to be like 0 bytes to quad, and I'm going to use AL. So that's the byte access. And I don't know if I need both this and this. For me, it should be enough just to specify the size of the register here. So I don't know if you're gonna need them. I think we tested it and it didn't work. I don't know why it didn't work. To RAX and move sign byte quad. All right, that's good. And this is a weird one. This is zeroing the top 4 bytes automatically. So I have to fill it in here. U64 to U64 is 0. So like null pointer. This one is 0. And this one is 0. So that's those. And I'm gonna interpret it as like cast from, cast to. So if I want to cast like a signed 8-bit number to a signed 8-bit, it is gonna be 0, isn't it? Cast sign 8-bit. I'm just gonna 0 extend. I don't really care about performance here. So I'm gonna sign extend from byte to quad. I'm gonna do like quad anyway. It doesn't matter. So for U8, I'm gonna do 0 byte quad. For S16, I'm gonna do 0 byte quad, because we want to take this value here and extend it to a quad. If it is a quad, it's valid for U16 as well. And this will 0 byte quad, sign extend byte quad, 0 byte quad, and sign byte quad. SBQ, CBQ. So that's this row, and the unsigned, that's gonna be the same. It's exactly the same. So this just tells where to move it from. Oh my god, this is gonna be boring. That's 2 of 4. No, 2 of 8. So from S16 to a signed 8. So you would assume we're gonna use like, this is S8, so we're gonna do like signed word to quad, but that doesn't make sense, because we're gonna only use, we're only interested in 8 bits. So this is still gonna be the same, like signed byte quad. And this is 0 byte quad. This, however, is gonna be sign word quad, because we're gonna move 16 bits. 0 word quad, and the same thing here. Sign word quad. And I guess this is the same in both columns. Or it is the same. Check chapter 312 something. 3123. Manual application programming. It's interesting. Okay, that's fine. Let's zoom in a little bit. Zero extend for Yes, that's not modified. That's fine. This is the one. Yeah, so it's 0x stands by default. That's why I'm using this weird instruction at the top here, this one. Software should explicitly assign extended result of 8-bit, 16-bit, and 32-bit to the full bit before using the result in 32-bit address calculations. So that's what we're doing. But we're doing it if it's converted to like an 8-bit or a 16-bit. We probably don't need to do that. But then we have to modify the load and store. I think the load and store supports loading from multiple or from like multiple widths. There is something we have to change for it. I can't remember it now. Thank you for following Lexum. Anyway, we're gonna just do this. Might be very slow, but it's fine. I don't really care. Like, I'm not gonna write any optimizer on x86 because I don't like the instruction set. I'm gonna write it on ARM though. So S32, this will be the same as this. SPQ, this will be the same. SPQ, SPQ, and SPQ. Oh, that's convenient. And we have 0BQ, word queue, and now we're going to use the long queue. So this will be, no, it's still one word. So here's the long. We're going to first do sign extend long to quad because we're going to convert S32 to S32. So normally this wouldn't require anything. But since we're gonna assume, I just want to make sure this always works, and I don't care about performance at the moment. So SLQ, CLQ. So that's the same for the rest. Here as well. Yeah, I think that's fine. I think that should work. U32 to S64. I don't really know how to test this. Instructions. So now we need to just emit the cast operator. Whatever. So it's going to cast from a type to a type. So we have to make sure this is a like, if it is a pointer, it's obviously U64. So, but if I'm casting from some kind of array, the actual, I'm having like a little bit of a stupid thing. Because in case of arrays, I'm actually modifying the size because of allocation. I probably should have two different variables for that. So the size actually, the variable should be, and the allocation size for the actual variable. I don't know. The problem is if you're gonna be on 32-bit platforms or 64-bit, you want to change that one single place, not like multiple places. What is the VS Code theme of the phone? I actually like this very much. We can switch though. I like all of these. It's very, very cool. It's called like Beta UI. Beta UI. It's really cool. I'm gonna be using green. Let's use this one. So we need to just emit the cast operator here. So I'm gonna first generate the cast expression, and then we're gonna emit this. So I need to get the index. Probably need to convert from the type I can make a function for it. Static. I want to return a U32. So this is get table index, and this is taking in a type. So I want to take in one of these types here, and I want to return, if it's, for example, use S16, it's going to return 012 or 012. So we're going to switch on the type size, I guess. And if it's pointers or arrays, it has to be handled separately, which is a little bit stupid at the moment. I'm gonna make a note of this. Array yeah. So I'm gonna just say if this is an array, basically type if type kind is equal to type pointer and type count. So we know it is a pointer and it points to multiple elements. So I'm going to be using this for dynamic arrays as well. But if this is the case, I'm just gonna give an error. Error token. Well, I don't have a token there. Get table index. That's fine. I'm just gonna assert 0. So I know where it is. And then we're gonna switch the size, because now all sizes should be valid. And we have like signed and unsigned. So let's make a bool assigned, and that is equal to type I want to have a signed variable. I'm gonna assume false. And if type is true, if type is basic and type basic is signed, is true. So now we should have this in signed variable. So if this is signed, we're gonna do a switch, and we can just say else there. We can do a switch here as well. So a pointer, I guess, is not signed. So here will be false. So if we like assume false, it's fine. I don't need to check for this. Yeah, type size. Okay. So then we can just check for this is sign number, because it's only the case if it's basic. And then I don't need this at all. That's far better. Okay. So if we have a size 1, we return. So this is assigned 1. This is S8. So that's 0. Index 0. Case 2. So 4 here. 2, 4, 8. So it's a 2 signed 2-bit. That's index number 2. So 0, 1, 2, 3, 4, 6. So it's 4 and 6. And then you have the same case here. It's going to be 1, 3, 5, 7. Making your own language too? Yes, I am. So this is going to be great. So this is getting the table index based on the type. We still have to track, like, if this type is a structure, like I probably want to. This is a cast expression. So this is only using cast. And if this is a cast, I probably know where it's wrong. Yes, I'm gonna check for this to be valid down here, because then I can like emit an error on the actual token. So I'm gonna say if cast2. Let's save the cast2 type. No. If cast2 kind is equal to inferred. So if the type is inferred, this shouldn't happen. It should have a stable type before this. So what stable types should be allowed? Pointer should be allowed, and basics. So I'm gonna say if this is not equal to type basic. Yeah. If this is not equal to type basic and pointer error token, we're gonna give the cast token. Cannot cast this expression. Wait a second, we're still gonna cast it. If this is like, what kind of types do we have? We have pointer is fine. We're gonna convert that. Type inferred, that's gonna be fixed later. Type unknown, it's gonna be resolved later. Type void pointer. I don't know what this is for. I probably added it very early. If this is a structure, it shouldn't be converted at all. So it should be an error. It should just be ignored, I guess. That's the generate a cast. So we have to assume the cast type is valid. I'm just gonna assert that the cast2 is valid and Thank you for following, by the way. So it asserts that it both has a valid type and it's being casted to a valid type. It's checking that. We're generating the expression, we have to do that anyway. And then we check if like, so what is happening if I have an array? It is switching on a type, so if I have something which is bigger, it's fine. I'm basically just switching on the size. So if I'm trying to load, like what I'm thinking, if I have data, which is 4 U64s. If I want to do cast data to a U8, is that even allowed? Let's check. I don't know if that's allowed. Because certainly if we just have these arrays, that's the only place I'm gonna have an array and not a pointer. So let's make an example in C. This is a little bit too small. So let's do like 10. There we go. I'm gonna just call it A. So int A is 10. And then you say I want a U64. Is this allowed? No, not I, A. That is allowed. What do they do here? So A will basically be a pointer to U30, to a 10. So I guess if the type is a pointer in general, it will eventually be converted to an address. So I guess it makes sense to just, yeah, so the pointer should be 8 as well. So this will not work for arrays. So I'm gonna have this assertion here. Like ideally, wait a second here. We have the pointer count here. And the pointer size will be 8. It is just the allocation which actually needs to know the total size here. So I think I'm going to replace the count should hold the number of elements, the size should hold the size of what it's pointing to. And if that again is a double pointer, yeah, that will propagate up. I guess that makes sense. So I'm gonna let in any pointer, so array or pointer, the size will be 8, or determined by the architecture. Yeah, let's fix that right away. I just have to remember where all those, like where it is, like all the places I'm using that. So here I'm parsing a type. If type is a open square, I'm saying current token there, number. Here I'm setting the count. Okay, so I'm not setting the size. I thought I did set the size there. If I did not set the size there, we have to remember, because now maybe the allocation is going to be wrong. So if I'm allocating stuff, it's probably going to be like 8 anyway. Yeah. Okay, so I'm still going to have it there. I'm probably going to remove it in 2 seconds. So I'm gonna say 2 is equal to get table index of cast 2. And from is get table index cast expression type. Thank you for following, Andrea Blom. Mol. So we're getting the index here. So I want to get this char pointer, which is table of whatever. So I'm gonna emit a string, which is this table of 2 and from, and this might be wrong, so let's double check. Thank you very much for following. I'm gonna cast from here, so basically from is this row, which is the last. So the from case needs to be here. Yeah, okay, so that's correct. Table to from, that's emitting the instruction. So I need to check if any of these are 0. I'm getting 0 there. I probably need to check it then. We can let this return like a minus instead. Yeah, let's just sign 8. And if this doesn't work, it's gonna return -1. I'm not sure this is the best way of doing it, to be honest. So this will be a signed 8-bit sign 8. And probably the GCC is gonna give me a warning on this. So if either 2 is equal to -1 or from is equal to -1, return. I'm gonna say if that's bigger than 0, then we do this. And I probably need a caster. Okay, it's not very pretty, but it should work. Yeah, it's gonna meet the instruction, which is what we're saying up here. That should be fine. Let's try it out. Probably have some errors now. What the hell? Initializer element is not constant. I'm getting error on all of them. I guess that was a problem. So you can't change this. Since I'm using these names directly, I can't change this one. So this will be like const char. It is a pointer to const char, and then the pointer is const, I guess. 127. Oops. Okay, so timing is failing. That's fine because we're not resolving the cast. I thought. Let's go into typer, and we're gonna type the cast expression. Type expression. Yeah, so typer expression is handle. I'm gonna change this to an assert instead. Assert 0, because then I know exactly where it is. So expression cast type typer. Are you using a window manager? No, I was using PowerToys before, and that was really good. But now I don't do any like window managers. I probably should though. Like if you want window managers, then PowerToys is the thing to use. It is very nice. I probably will install it again. If it is for Windows then. There is a uint pointer in stdint. Why should I use that? Or the build? Oh, the build is very wrong. The build is very old. It's from the OS I was developing. I'm gonna change the info. So type cast expression. Let's do it here. And also yesterday I found a few mistakes here, so we have to fix those as well. You're gonna type a cast expression. First of all, if the expression already has been typed, we're gonna just return. Thank you for following. So if type is something, we're gonna return. And then I'm gonna get the cast. And we have cast to, cast token, cast expression. So I'm gonna first recursively call cast expression. So type expression. Cast expression. And that should also return if it doesn't work. So at this point, that is checking the expression. So this doesn't need to resolve anything, so we have to check it here as well. So if type expression, no, if cast expression is equal to 0. So if this hasn't resolved this type, I need to think if I had to mark it as like unresolved. I think a little bit unsure. Like we could do like typer unresolved type is equal to true. I don't know if we're gonna need it. And just return because we can't do anything else. So at this point, we know that the cast expression, so basically when I'm writing something like this, I know that this expression has a type. So this has a type. Which is not really necessary. Because we know that this cast node is going to have the same type as this, which I probably know. So I need to resolve this type here. And then the reason I need to resolve it is because sometimes I'm using references to structures. So that's just a name and I have to pop in the actual structure. And sometimes it's an inferred type, so I don't know the type yet. But in this case, it might be an unknown type. So like a struct type. So in case of this, this is now unknown. And eventually, this is going to be filled in with some struct to whatever members and so on. So after this has happened, we can set the type of this entire thing. So this is like something, I just have to make sure this is being true. It isn't really a return. I'm just gonna make sure this is happening. Type expression. I'm gonna move this in here. No, not really. I feel I need to know if I have to do this. So type expression, it will do all this. So primary expression. I'm gonna guess I'm actually filling it out this correctly. We're gonna go through the code and see later. So just as let's just assume this is happening. So then I can move this down here. So basically, if the expression I'm casting is not typed, I'm gonna type it. I'm gonna try to type it, and this will fill out the typer stuff for me because I'm doing this. So that's the first part. I don't really need to track the results from this part. The cast expression also has a cast2, which is just a type. And we have a resolved type. It takes in a type and returns a type. So how do we know if this is resolved? This is a pointer to a type. So I'm basically gonna say that I think I can just like this is a type which is just a pointer. So I can set this expression to point to the same thing as this right away. It is going to be resolved eventually. I just need to think. Do I need to make sure that is happening? I'm going to make a little note for myself so I can go back to that later. Okay. So I'm gonna just check if this is being if this is happening. So first I'm gonna make a bool which is unresolved types. I'm gonna say save. Holy fuck for a difficult word. Unresolved save is equal to typer typer unresolved types. I'm gonna save this one. And then I'm doing unresolved is equal to false. Then I can check if it's being set in this function. And then I'm gonna say cast2 equals resolve type of cast2 typer, and then I need to change this back. So I'm going to say typer unresolved is equal to what it is, or this one. So I'm going to do this. That will resolve it. Like if this is false and it was true, it's going to set it to true. And if this is true and it was false, it's going to still be true. But the thing is that after this, I can actually see if this has been resolved. So if unresolved types is still false, I know that this is fully typed. So we can do like typer. If that is false, this might not be the best way of doing it, but it should be fine. So that's false. I'm gonna say like type has been completely. So I'm just propagating the expression type, which is equal to cast2. All right, so now the expression has a type, so next time it will just do this. It might still need to do this here first. So I'm gonna check this later. I'm gonna check it here. So I'm gonna do this until this has been typed, and then I'm gonna return if the expression already have a type. Because this here might happen before this is happening. So to avoid any problems there, we're gonna do this after. I'm usually taking this before, but I think that should be fine. So try to resolve the type. No, never mind. False, and restore it here. I think that should work. So it's typing it completely. Let's see what the code looks like. So I'm casting some, okay, so argument count is a U64. And I'm casting this to a pointer to 32 U32s. So argument count is a U8, and I'm casting it to this. So this is gonna make sure that this cast node has the type pointer to array to 4 bytes. This is unsigned. And then that plus, so this is gonna propagate up here. That's also working. And this is casting the binary to an unsigned 8 bytes, so this is gonna be an unsigned 8 bytes. It seems like all the nodes is being handled. I don't know. Output 28. We have a 0. It's probably casting between like a pointer, which is U64, and just a U64. So basically we're hitting this one with 0. Nah, let's save this as a string instead. Cast code is equal to this. If cast code cast code. So this will make sure it only happens when it's supposed to. So we have error 81. I don't think I'm returning anything. So yeah, I think 81 should be fine. Return 0, and it works. This is cool. So now I guess casting is working. So now I have to just test it. Yeah, and this is the problem with the array size. So I think now, if I'm gonna try to allocate some data here, which is an array. So this is gonna be an array of, I'm gonna say 50 U64s. I'm gonna say 50 U16, so it's gonna be 100 bytes. And I'm gonna do the same in global scope. And I can use the same variable, that's fine. So let's try this. So now we have data, global scope, which is 8. So this has the wrong size, and that's because I'm not multiplying it by the number of elements. Which is a little bit like weird. I have to recurse in the generator. I don't know if I like that. Let's check if this has the right size as well. Not the wrong size as well. So this is when I set up the offsets. So I'm doing plus equal the declaration type size. So this is in fact also wrong. So we say stack frame, and then we print the variable name, and then we print the size. So it's assigning 8 bytes for the data, which is wrong. This is strange. I'm gonna do 50 of 50 instead. 10 of 50. So this should be like 1000 bytes. It will still be the same thing, but now I have to change those. So the size here will be wrong. I don't know. I don't know. It's just that the pointers and arrays are very similar, but they have a different allocation size. I can make a new variable, or I can just resolve it here. I can make a function for getting the allocation size based on a type. I've added a note on this, so I probably will change it later. So get the allocation size from a type, and this will return a U32. Get allocation size. So this is going to be a recursive thing. So if type kind is equal to type pointer and type pointer count. So if it is an array with multiple elements, or if it is an array, like the base case will be here. I'm returning the type size. And here I'm gonna return, there has to be some multiplication here. Let me see. When you make something like this and you type EU32 or char, how do you program the data type into ASM or binary? Do you translate to C types? I'm really, the only thing I'm doing is that all standard types, so like char, U32 and stuff like that, it has two variables, which is, one is signed, it determines if the number is signed, and the second one is the size of it. So that's the only thing I'm tracking. And for structures, it's a different thing. It's a separate structure for like unions and structures. So it's only like basic types I'm actually tracking the size. Or I'm tracking it for everything, but for basic types it's only like, what you ask about is I'm just tracking the size and the signed and the signness on it. Yep. Print declaration type size. What does that mean? Doesn't the compiler choose what gets allocated? Does the compiler choose what's get allocated the CPU, cache, or RAM? It can only choose for RAM, so it's going to be allocated into RAM. There is probably some pre-fetching stuff which can fetch things into the cache. Some instructions you can choose, but I'm not going to do that. Pointers always be the same size. Yeah, that's correct. But the allocation size might still be different. So I need to get the allocation size here. Right. So if this is a pointer, I'm gonna return type pointer count times get allocation, get allocation size of type pointer 2. So you're gonna recurse here. So we're checking what this is pointing to, allocation size. And this will eventually terminate here. So just get the base size and then you recurse up. So if I'm instead of type size, if I'm instead using this one, it should probably work. I'm gonna just copy it in here. Oops. Segmentation faults. Pointer. Oh, get allocation size. Pointer count. That's strange. Like, we have some warnings here. Oh, yeah, we're calling it with something wrong. So I'm gonna just give it the type. So now we're actually fixing the data allocation, which is 1000. So let's do the same thing with the global allocation, because it's kind of the same thing. So the global allocation, where the fuck is that happening? I'm getting so deoriented here. Compute local variable offsets. Where's the global thing happening? Error declaration. I think it says a statement. It's an expression, like a compound probably. And then you generate... What the hell? I'm doing something with scopes here. Generate scope, that's probably it. Yeah, so here's global scope. So if the scope parent is 0, which is a global scope, then you go over all the variables and you allocate them. And this is not initializing them. So this is just gonna 0 it. So instead of doing declaration type size, I'm gonna do get allocation size declaration type. So now I should also have like data which is 100 instead of 8. And everything will be still working. So this is very nice. I might still change it though. I don't know. This is working. Let's write some code for this. As we're gonna be making some local variables. I don't know what direction I'm adding those. I think I'm adding those in, let's initialize them. I'm adding those last in the list. So they're just pushed on the scope. Let's check how they are pushed on the scope. Parser. There's a declaration parser somewhere. Parse struct declaration. Parse just declaration is here. And if this is a variable, I'm doing this. So I'm pushing this on the current scope, which is doing push on scope, which is getting the list, and we're adding it last. So it will be added in order. So this will have this will be assigned first, and since the stack grows downwards, it is basically going to be like this first and this and this. So I'm going to switch the order. So ABC. And then I'm going to make a structure. So I'm going to call it test. And this has a which is a U64, B, which is a U64, and C, which is also a U64. So now let's just try to print these variables first. A, B, and C. So we're getting 1 through 3. So now we're gonna, instead of accessing those by the variable, we're gonna access it by a pointer. So I'm gonna first make, I'm gonna make a new object. I'm gonna say test is gonna be a pointer at, I'm gonna say variable. Variable is a pointer to test, which is a pointer to this structure. And it's gonna have the address of, it's gonna have the address of A. Now this will not work because the address of A will be a pointer to U64. So if the typer had worked correctly, I would have to cast this or use some kind of autocast. So the correct way of doing this will be cast pointer of A to pointer to test. And this is very cool. You have the same syntax here. And then you just say variable A and variable B and variable C. And it's very cool. You can just do dot here. You don't need to do arrow. And it works. It actually works. Oh, dang it. It works really well. That's so cool. That's very cool. Thank you for following. Thank you very much. Why 0, 100? That's because I'm using 100 here and 1000 here. This is a 2D array, this is a 1D array. It's just a different allocation size. You made for the ARM Cortex? Yeah. So, I don't know what it's called. I can't remember. But I was starting on a new operating system for like a few months ago. And I stopped because I wanted to make a compiler. So that would probably, I would probably delete that that project, and I want to start again. And I don't want to write for everything. I want to keep it simple, like make it for one single chip. That's what I'm interested in. But yeah, that's gonna happen very soon. Got my interpreter running. That's very cool. Binary operations are running. So cool. Congratulations. It's nice to hear. Yeah. Okay, let's double check the casting. So if I'm not mistaken, if I do this, let's do 500. Then I will be a U64. So if I print I here, this is just for testing if the casting is working. If I print I, it will go from 0 to 500, which is working. So let's assume I want to cast this to a cast I to a signed 8-bit number. So then it's going to go from 0 to 128 and then down to like minus something. Bad register name AL. Why is that a bad register name? Why is that bad? It's complaining about this. Byte quad. Let's see an example of this. BL. Oh. I think I'm doing like two percentage signs after each other. I don't know. This is normally used for escaping stuff. Yeah, I'm using 2 of those. So this is supposed to be just 1. Okay. And it seems to get negative values. So the casting seems to work. We're actually casting it correctly here. To 100 and it goes down. Okay, yeah. So 127. And if I would cast it to an unsigned 8-bit, it's gonna be this. Perfect. This is so cool. So I think we can start implementing some cool stuff now. Actually, very much is complete here. The next thing I sort of want to look at is making out some kind of interpreter, because I don't want to have make, because I absolutely hate make. So I want to be able to build stuff, and I'm not really sure I need an interpreter. I could just add the files. That's very simple. But if you want to do some kind of make stuff, you want to do some string operations, I want to add like all the files which ends with some certain extension. You probably want to be able to run like some small amount of code when you build stuff. So I want to implement that, because then I can implement multiple files. So that is the next thing. Wait a second. Also, this is not aligned. We have to align this. Let's just fix the alignment first. So global emit. So above this, we're gonna emit align, and that will be type alignments. I deleted it. Dang it. Okay, so now this is aligned by 8. So if this was a oh, that is also wrong, because this is not that. This is supposed to be what it's pointing to. So this is the base type. So the same way I need to make a function for getting the alignment of a type. There we go. Allocation size. And we want allocation alignments. Yeah, I guess it's the same. So if it's sort of the same, it's not going to recurse that, or it's going to recurse, but alignments. We're not going to multiply here. We're just going to call it the same function. And eventually it's going to return a value. So we get the allocation alignments, pointer to. That's the count. Yeah, that's probably right. And this is just for arrays, which is a little bit weird. So now we're getting 2 here, which is right. I'm gonna align with 2 bytes because I'm having a U16. That's perfect. Very nice. Is it GNU licensed? I don't know. To compile in the system itself. Compile, yeah, it's gonna be cool. I don't know what the license is. I've just added the copyright notice. I don't really care. I probably shouldn't make a license or something. I don't know. Yes, we're using the same as byte codes. Seems reasonable. Very reasonable. All right. Let's make something cool. I was gonna make an allocator. So this is the one I'm using in all the operating systems. It's a really cool allocator. It's based on like linked lists. So it's used for small allocation sizes. So this will sort of check if this is working correctly. Which is the clock? 40:40. That's perfect. Okay. So how does an allocator work? Allocator. Okay. So what we're gonna do, we're gonna have a big region in memory, which you're gonna pre-allocate, which is gonna be used for the allocation. So normally in like if you're doing malloc and in C, then the standard library just asks the OS for memory. So it's not pre-allocated, it just asks for, I think it called set break or something, SRBK. It basically asks for memory. And once you have the memory, you're gonna make sure you can allocate from this memory. And how this works is you're gonna insert some small blocks of memory. You're gonna set aside small blocks, which is gonna be called metadata. Metadata, I don't know what it's called. It's like an info block, which is telling the size of the block, and it's a pointer to the next block. So we're gonna insert one here. This will be like 2 pointers, so a size and a pointer to the next one. We're gonna insert one here, and we're gonna allocate one here. So I'm gonna say A here, because we're gonna allocate it. So not allocating this one and this one, because it's already allocated. It's the same region. We just say that at this address, it's supposed to be a block like this. And then we're gonna make this link. So this is gonna point to the first one, and the first one is gonna point to the last one. And this is gonna point to 0. So this is the initial state of the allocator. And also note that each of these blocks is gonna have the size and a pointer to the next one. So this is containing the size of this region here. This is containing the size 0, and this is containing the size 0. So if you want to allocate some data, right? If you want to allocate, let's say 10 bytes, allocate 10 bytes. The first thing you have to do, each single block is going to contain some data before it. So the first thing you have to do, you have to increment it with this block here. So the size of this, so the size of every block will be the size of the free region plus the size of the descriptor itself, which is the blue thing. So the size of this will be from, let's see, from here to here. Okay. As I'm adding this, I'm increasing the size, adding it like 8 or something. And then I'm gonna start iterating from this node here. I'm having this like dummy node. This isn't really, I'm gonna call it dummy node. So this is only used for making it more convenient to do double iterations, because many times in this implementation we want to have the pointer to the next one and the previous one. So by having this the start link here, I can say this is the next one and this is the previous one, and then I can do the double iteration through. So we're gonna start here, and we're gonna check if this can fit in here. And if this can fit in here, yeah, we're gonna like iterate, and for each block we're gonna see if this can fit. So if this can fit in here, we're gonna check 2 things. So the first thing we're gonna do is just eliminate those pointers. We're gonna do this. This is not gonna be linked anymore. So this is the state now. And then we need to check if this remaining size is big enough to contain another allocation. So in this case, it's way bigger than we need. So we're gonna insert one block here. And we're not allocating anything. This is just, we say to the compiler, at this address, it is supposed to be a structure. So inserting a block here. And then we're gonna insert this free block, and this will obviously have the size of this remaining region. So now we're gonna insert that block into this allocator. So that's being done by setting this to point here and this to point here. So now we have a used block here and a free block here. Also, we are only tracking free blocks. So if it's a used block, we don't track it. This is a linked list of free allocation units. So let's make a more complicated example. So assume we have some allocations and deallocations, a few of them. So we have a free block here, and we have a use block between those. So now this will point up here. This will point, I guess blue is a bad color. I usually do green for those. Now this case will not happen. Yeah, that case might happen. Yeah, that might happen. Never mind. This node is not really valid. So this is the case we have now. So this like this is used. I'm just marking it here. It is probably simpler to understand by just I'm gonna mark it as green instead. It's a little bit simpler. There we go. And this is used. Okay, so this is the state. We have some allocations and we have some, so these regions has been freed. So this is the state. If you want to allocate something from here, you're gonna construct, you're not gonna construct it, you're gonna just check the size of it. You're gonna check the size of what you're gonna allocate, and then you iterate through the entire list. So you're gonna check like, can it fit in here? No. So you go to the next one. Can it fit in here? No. So we have a fit here, and then we can insert it here. So what happens if we're gonna free some kind of memory? If I want to free something. This is allocated, so the user contains or has this pointer here. So now the user calls free with this pointer. So what do? Like, you have to know this block here, because this block is gonna tell you, the size. I don't know if we really need a size. No, you don't. I can't remember. We're gonna take a look at it. But basically, you move this pointer. You move it over here. So that now you know you can obtain this block here. And the only thing you do is you insert this block into the free list. That's the only thing you do. So that will make a green block here. And this pointer is now going to point here, and this will point here. Now this is obviously very inefficient, because you have 3 blocks which is directly adjacent, and if you're going to allocate something which is like decently big, that's a bad word, something like this, it doesn't work, because you're going to check this block here and this block here and this block here. So what you want to do, you want to combine those. You want to make one single big block out of all this. So when actually inserting those blocks, you have to check the previous one. So you want to check if this pointer here plus the size is equal to this new pointer. And if it is, you're going to combine them. So I don't know if that's understandable. That's how it works. So you're going to try to implement that. Any question? If not, I'm going to just start implementing it and see if it works. Like we have, I used to find this very hard. I think the last time I did it, I struggled very much with it. I don't know. We have kind of like two things that can go wrong. We have the compiler, which I'm not sure is going to work, and we have the algorithm, which I'm not super stable at either. So I have to see. Anyway, we're gonna just allocate the memory statically. So I'm gonna make a buffer and we have a size for it. And I think I can't evaluate any constant expressions yet. So I have to just write a number, but that's fine. So I'm gonna allocate a buffer, which is, let's say 1024 bytes. So now I'm gonna have 1024 here. And then we're gonna initialize the allocator. I'm gonna give it the pointer and the size. So I want to make a function. This is already the allocator. Allocator implementation. Hello, regular Cobalt. Welcome to the stream. So we need an allocator init, which is a function, and it takes in the pointer. Fuck, we had to implement void pointers. Let's implement void pointers real quick. I think I have a type for it. I made that, but I didn't implement it. It's a void pointer. Now, do I really need a separate type for this? It is just a... I think I'm gonna remove this. I'm gonna just keep the pointer. And if this is a void pointer, what is pointing to is 0. So we might need to check that a few places. But I think that's the best way. Okay. So in the parser, there we go. So I'm checking if for multiplication. So this is a pointer. Let's add weak pointers as well, like the question mark. It's they're basically going to do the same. So I can just check for both. Token question wouldn't have question. Elixir. I'm gonna add question down here. Question mark. Then the Elixir needs to add a question mark. Token question. JMalloc, what is JMalloc? What are you studying at what university? I'm studying at NTNU in Norway. I think it's called like Electronic System Design and Innovation. Yeah, so like electronics. It's the BSD allocator. That's cool. Is it like a, what kind of allocator is it? Like what type of allocator is it? Visual Studio keeps crashing. I'm not surprised. Locality and memory in consideration. That's cool. But that's more advanced though. So now we have the question mark. So we can check if this is either multiplication or question. And then we have to mark it as weak somewhere. So this is only for pointers. So I think in the beginning, I want to mark it here as is weak. So like a weak pointer is a normal pointer, but it can be 0. So you have to check it first. And the compiler is gonna know when you check it. So now we have 2 cases here. You might check it and do something in a statement. It is really the dereference which is dangerous here. We can use it. It's the dereference which shouldn't be done. So let's just have an is weak. So everything is going to be the same. Pointer is weak. That is equal to token kind equals token question. So if the token kind is a question, then this is a weak one. Like maybe I should do if this true, otherwise false. It doesn't matter here, but it depends on how these are defined. I think true is defined to be 1. Yeah. So that's really the only thing. The problem is we're actually parsing a type. So with this new change, we're not gonna force a type. If it isn't a type after, it is just a void pointer. So I need to check if something is a type. Dang it, I'm gonna have to copy this entire thing. And you should be able to say like that's a double pointer. So you want to check pointer to yeah, if it's not a type, if it is none of those, you're gonna return some. Otherwise, you're just gonna parse it again. Yeah, so it's gonna be like everything. We need to check if it's one of these. Thank you for following. Welcome to the stream. Is type. Is type. So what are we gonna call it with? We're gonna call it with we're gonna call it with a token. Yeah, let's call it with a token. Yeah. And then we have to match all of these. Let's just do this. Return false. It's going to return in any of these cases here. Thank you for following. Thank you very much. This is kind of bad to do. I don't know. I just feel like I'm doing something I'm not supposed to do. So it's going to check if a token is a type. And pointer to might also be 0. It's going to parse a new type. Do we need to do that? Yeah, because this is supposed to have an error. I could return like 0 here, but then I need to probably specify the error like multiple places, and I don't want to do that. So we want to check the token first. So this is token kind, and we're consuming this token. So token is already pointing to the next, or the lecture is already pointing to the next token. So I can do token equals current token lecture if there we go. I don't think this is necessary, but I'm gonna do it still. See, if it's pointing to something, you're parsing the type. Otherwise, you're just having 0. Yeah, an open square is parsing a type. Cool, very cool. So now I'm gonna search on pointer2, because this is gonna probably fail. I have to have a check for it. Get allocation size pointer2. Yeah, now this doesn't work because it doesn't point to anything. Thank you for following. So this really shouldn't happen. This is a fault if this is a void pointer. So if that is 0, do I have a token here? Type. I don't have a token. Pointer2 is an error. So probably I should store. I need to know what this is pointing. Like I have to know where I'm gonna issue this error. I can probably fix it elsewhere. This is allocation size. Can I use declaration size instead? Declaration type. I'm gonna do declaration instead. Get allocation size of just a declaration, because then I can issue an error on this declaration instead. So declaration, and then you just do declaration type on all of them. Yeah, it's probably fine. So declaration type here as well. Declaration type, declaration type. All right. So basically now we can check this and see if this is not valid. So now we can just use declaration. We should have a token here. Name token. Cannot allocate this variable. This is probably going to specify something a little bit more readable. But that is very readable for us when we're making this compiler. So if pointer is 0, cannot access this variable. Cannot allocate this variable. Cannot allocate, so I'm going to be more expressive here. A void pointer. So I'm checking it here. That's fine, it's fine in the parser. So in the tree printer, I need to check if this is valid. So if type pointer to, so if the type is valid, we just print it. Otherwise, we print probably indented print. I'm gonna say just void pointer. Just void pointer. This is printing it now. This is gonna be this is giving pointer 2. Ah, okay, that's fine. So that's good. The typer, we need to fix in the typer as well. So we can't directly do this. So this is in case of binary plus. So I don't even see, I don't think you should be able to do like arithmetic on void pointers, because plus and minus on pointers is really determined by what it's pointing to. And if it's not pointing to something, you can't really change the address with the correct amount. So before I'm doing binary minus and binary plus, you can't really do multiplication either. So this is just checking if it's a pointer. That's fine. This is just swapping it. So if this is happening, then we have, if this is happening, we have the pointer is at the left hand side. Yeah, left hand side. So now we can check if binary left. We already know this is a pointer because we're checking it up here. If pointer 2 is equal to 0, error token do I know what this is pointing to? Pointer 2. You have to have a token here as well. I can use the binary token. I'm going to use the binary operator. I cannot use this operator with void pointer. Thank you for following. Null pointer exception. Is your allocator going to be NUMA very? No. Not at all. It's gonna be single core. Single core, simple. It's just for testing. Like, it is not really for making an allocator. It's just for testing if the compiler is working with something which is more complicated than printing. Yeah, cool. If it is minus, assert 0. We haven't implemented minus yet. That's that one. So we check that that's actually valid. And then we have type unary expression. Okay, so we say if this is the address of, this is making a new pointer. That is fine. This one is not fine. So if you try to dereference, this is basically dereference a void pointer. Operand pointer pointer 2. If that is 0, then we give an error on the unary operator. Cannot reference a void pointer. Dereference a void pointer. Is that one? No. Yeah, so that way I fix this one. If it's a string, it's basically making a new pointer. That's fine. If I'm typing dot expression. Now here, I have to think. Oh my god. It is checking what it's pointing to. Like what I'm thinking, am I checking this somewhere else? So we first have to type the expression. So if this expression is some kind of cas expression and then you do the dots, then this will be valid. So I'm gonna add it here as well. It is never gonna happen though. Dot token. So basically what the user is trying to perform the struct member access of is a void pointer. Cannot access member of a void pointer. And then we resolve a type. Pointer 2 is resolve type, is just recursing in there. So if pointer to is 0, it's probably just should return. Yeah. Pointer 2. Break. I don't like this. I don't like this at all. I'm gonna say if it's pointing to something valid, I'm gonna resolve it. Oops. That's better. I think that was the last one. Yeah. So now everything is handled. Now it should work with just void pointers. They should work. So let's try to make a data, which is a void pointer, and it's equal to some number, and then you do test, invert, assign, what's at data. Oh. New type. Oh, return type. That's the return, like that's the void. It's for the I thought it was for the actual types. So I have to add it back. Type void. Cannot dereference a void pointer, so that's good. That's very good. We have some errors first. Pointer to allocation size. Oh, I'm doing wrong. That's wrong. No, in generator. So this is not taking in a declaration instead. So I should be calling this with it doesn't really make sense to take in the declaration there. Get allocation size. I'm gonna return a signed. Maybe you can allocate it very much. I'm gonna return a signed 64 bits. That should be plenty. And then just return -1 if it's failing. Because I can't. I have to call it with the next type, so this argument has to be a type. It's a little bit like stupid. It should have multiple return values, and I'm gonna implement that. So you can implement, like, you can have a status and you can have a size. That's much more clean. Yeah, it's single threaded. Hello, Adam Automatic Log. Welcome to the stream. So then this is gonna be simpler. This is just the type. And we do not error here. So this is gonna be removed. Get allocation size. Okay, I think that's it. Type kind, yeah. So now this is taking in a declaration type. We have to first save it. If size is less than 0, you say error token, declaration, name token, cannot allocate a void pointer. And then just plus it with a size, cast it to a U64. Okay. And we need it here as well. So this is going to be declaration S64 size, S64 align. Get allocation size and get allocation. No, get allocation size is going to go here. There we go. Get allocation alignment. Does this take in the size? This is just gonna take in the declaration type, I guess. I don't know why it said size here. It's really weird. Size and alignment. A64, A64. Get allocation size. Yeah, so this is a void pointer. Thank you for following. But it's gonna recurse up here. Get allocation size. This will still be negative though. If the allocation size is negative. I'm gonna check that. I'm gonna fix this later. Let's just keep it simple. So return -1, so it's gonna be negative. And the same should happen here. So now we need to check if one of those are negative. All right. Cannot allocate a void pointer. Is this right? The size. If it's pointing to 0, this is happening if it's a count, but it shouldn't be a problem really. Well, a void pointer shouldn't have a count. A void pointer, if this is a void pointer, the count should be 0. Because if the count is something, then you have this, and that's not a void pointer. That's a pointer to, for example, a void pointer. That's fine, but it's not a void pointer itself. So both of these will work. So we're gonna just assert it. And this can also probably be done in the typer, because I really don't want to check it here. So I'm gonna just say move to typer. All right. So now there's going to be U64. There's going to be U64. The rest is the same. And we can just do this. It's actually making it simpler. The allocation size. That's here. All right, I think that should work. $560. no, that's only type. There we go, so no errors, that's fine. And also, let's enable this. I want to see what the stack is allocating. It's not allocating anything yet because we have an error. So let's dereference variable is a u32, which is a value. And then this pointer is the address of variable. And this won't work. But if you cast this to something valid, so you're going to cast data to a pointer to u32, that's going to work. And that's going to give you tests, which is an unsigned 4-byte because we're inferring this size here. And we're getting the correct value, so that's perfect. So now the void pointer is working. That's really cool. Let's try to do like data plus something. Oops, you cannot use this operator with a void pointer. So data is a void. Here I could probably say, I can probably highlight this left-hand side. But that requires more because this might be something bigger. This might be an expression in itself. So I want to be able to, I want the error handling to be a little bit better. But this is fine for now. Very good. What more can we do with a pointer? I don't think we could do anything more. Let's try question mark pointer, which should work the same. Yeah, it's a pointer. Where this is a pointer to unsigned 4 bytes. Okay, that's not it. Here we go. So this is a pointer to unsigned 4 bytes. This is a pointer to void pointer. Okay, that doesn't make any sense. This is a pointer to void pointer. Okay, so this is in the print type. In here. So I guess I'm printing pointer to somewhere. Here I'm printing pointer to. Thank you for following. So I guess I want to do it at the very top and just break. I don't know. I also want to say if the pointer is weak. I'm just gonna so this I'm gonna say a char here. I'm gonna string there. So if pointer is weak, I want that to have like, I'm gonna say char c is equal to if pointer is weak, if the pointer is weak, that's going to be a lowercase p. Otherwise, it's going to be a uppercase p. And then we have a const char pointer string, which is equal to if type pointer is weak. It's going to be weak. Otherwise, it's just going to be nothing. So then we have string NC. So that's going to print the correct pointer. Thank you for following. Yeah, dang it, I'm just going to print this at the very top. Oops. So I'm checking if this is equal to 0. Then print the void pointer. Pointer to void. No, that's fine. I'm gonna have it like this. I'm gonna say nothing. Pointer to nothing. Dang it, I'm gonna say void. So now we're getting, this is a pointer to void, and the pointer is wrong. We have a space there. So I'm gonna do this and weak space. So pointer to void, I should have a weak pointer here as well. Where is my weak pointer? Data is defined as a pointer to. So this is supposed to be a weak pointer. I'm setting, if this is equal to the token question. Oh, I'm moving the token. The token is not right anymore. So I have to move this up before that point. So now we're going to have a weak pointer to void. So a weak pointer, we have to check a weak pointer first. So I have to mark it, and that might be a little bit annoying to do. So we can detect something like, if I have a weak pointer and I check that with 0, this guy, I can detect this one. So after this, I will say like data is a weak pointer. So after I've checked that data, if data is equal to 0, I can do this. I don't think I want to enforce anything more. Like the user is just going to check it. Yeah, so I have to detect this if this is happening before. So what I'm gonna do if this is happening, because I'm basically gonna switch the data type here from weak to being strong. So I'm gonna clear the is weak bit. But if I clear it at this point, then it will be strong in here. So if I would try to do something like this, it doesn't work. But I mean, the user should probably know that that's a bad ID. Like if data is equal to 0, then dereference. That's like horrible ID. So I don't know if I'm gonna check it. Additionally, the user might want to do like if data, see if it's valid. Then it should be used only in here. So then this should be fine. So this should be error. This should be okay. Yeah, this might be different. So I have to somehow track the scope. I need to know the scope thing. 2 seconds. gonna sit down instead. Could you track the pointer assignments? Data flow, we can track that, definitely. So we can, like, we have everything, and we're pausing over this multiple times, so we can definitely track this case. The problem is like the if statement. It is very easy to just enforce this. That is very simple. But how do we know that we're in a scope? Maybe I have to do some additional... I feel this would require some additional data structures, like placing the weak pointer in some kind of list. Maybe adding maybe I'm thinking too complicated now. I don't know. So maybe add a list node here so we can place the pointer itself in a list. And when we when we exit the scope, we should set every I haven't really thought of it. We could just start by doing this. Check against 0. Like, I mean, if it's 0. So the user should be able to do this. I don't know if that makes sense, but it's very simple to like just check that it's actually being checked. Maybe keep track of the conditions that have to be met for a certain code path to be executed. Conditions that have to be met for a certain code path to be executed. Yes. Yeah, I'm also thinking something like that. Because if you're dereferencing it here, like this might be more complicated. This might be like, let's say like if, just ignore this, if 5, if 4, while true, then we check if data is equal to 0, and then we try to dereference it here. Or maybe we do this up here. It doesn't really make sense if it's gonna make it more complicated. I think it's still the same algorithm. So the question is, what happens if you choose to do this? That's interesting. You're checking against 0 at this point, so there would be need to track the code path somehow, because I can't just set it to strong after checking this, because this if statement might not be true. So I would be forced to evaluate this at compile time. It is not really, that's not really how you use it. It is intended to track places when you take in a void pointer and you don't check the type. You know what, we're gonna just try to implement the simplest case. Checking for 0 should only make the usage valid. Yeah, that's right. See, if I'm returning here, that should still be valid. I don't know, I haven't given it enough thought, so I'm gonna take a look at it, think a little bit. We're gonna try to just catch the simplest case, the absolutely simplest case. And this might be wrong, so I'm gonna comment that it's wrong. So this is in a typer. Let's go up to binary expression. That's binary. So at this point, everything has been typed. So we check if the first one is weak. Static is weak. That's going to return if no, this is going to do the type. Expression type kind equals type pointer, and expression type pointer is weak. Thank you for following. So we have two cases. We have the first one, the left being weak, and the second one being 0. We can also like check the is 0. And we're not having not. We can probably check that as well. It's going to require some more logic. I'm going to just do the simplest case, just to get something that works. If expression type, if expression kind equals expression primary, and expression primary kind equal primary number, and expression primary number is 0. So that is 0. So if the left one is weak, and so this is happening if it's unassigned. So if binary kind is equal to binary assign, so if the left one is weak and the right one is 0, or the other way, so left and right, error token no, it's not gonna give an error. So here we're basically checking for 0. I'm gonna just mark this as wrong. So here we're checking for 0. So now we're gonna say that we kind of have to do it in two different places. So here I'm gonna say binary right type pointer is weak is equal to false. and this will be left. Now we're gonna check it for the unary type. So in case we have a deref, it should have a pointer too, first of all, and this is a dereference. We're gonna check if it's a pointer. It's not equal to type pointer. Yeah, if it's not equal to type pointer, it can give an error. Error token unary operator cannot deref a something not a pointer. So that's the deref thing, and then we check for the weak pointer. If type pointer is weak, so why this works, like there is no such thing as array in the actual generator or in the typer. I'm basically converting all array accesses to pointer access. So this will track arrays as well. Error token unary token cannot deref a weak pointer. Thank you for following. No, I'm not implementing smart pointers. This is just something for I don't know why I'm doing this. Get allocations are not correct. Check array of. Okay, 2 seconds. I think this is correct now. Generator. Get allocation size. Check array of endpointers to U8. What do you mean? Endpointers to U8. Okay. Let's allocate a list of 10 pointers to U8. Signing. This will have 80. That is correct. The size of this is 8. This is going to be 80. What do you mean? I think this is correct. Yeah, some Rust style thing, pointers. Some really shitty one now. It isn't really working yet. Let's try to... Data is now a... Let's try to dereference data. Then it's gonna give me cannot dereference the void pointers. That's the first error. Okay, so let's make it a not the void pointer. It's gonna point to something. Then cannot dereference a weak pointer because I haven't checked it. If I'm doing... We have also to check if this is being done after it's initialized. If it's declared here, and I have to mark some... This is going to be more complicated than I thought, but it's probably fine. If data is equal to 0, return. Cannot derefer. What the fuck? Till the 0. I'm not tracking this. Type binary. If it's equal to binary assign. No, this is not assign, this is compare. Equal. Then it's gonna work. Okay, perfect. Yeah. It's not like optimal, but it certainly should work. For the testing purposes. So now we're gonna actually start implementing this allocator. So here we have a buffer, and we want an allocator in it. This is a function. Thank you for following. This should take in a pointer, which is just a pointer. It doesn't matter what it points to. And it's a strong pointer, it should be valid. And then it takes in the size. Alright, so first I want to make some structures. Actually, we want to have two structures, one for the node. So one for this kind of thing, this info block, and one for the entire allocator. So we're going to say allocator is a typedef struct, and then we have, it is very weird, like I would actually place the info block up here because I'm going to use the info block down here, but that doesn't matter. That's really cool. Let's actually just big capital A. Let's call this block info. So the block info is going to contain the size, and it's going to contain a pointer to the next block. So I'm going to say next, and this is a pointer to block info. And so the allocator needs to include, I wanted to include pointers to the first one, pointer to this one, and pointers to this one. And I also wanted to allocate this object for me. So I'm gonna first have a block info So I'm going to say dummy block, and that's an actual block. And then we have a start pointer, info, and we have an end pointer, which is both pointing to blocks. And we can also track like allocation information here, like how much, like stats, I guess. But let's keep it simple. So we just have this. I'm also going to allocate a new allocator. Allocator is an allocator. All right. So actually this function here is going to use this global object. Allocator. So let's initialize this. This is a pointer. I need to align the start and stop address with something that we No, I'm just gonna manually say that this block is 16 bytes. The next thing we want to implement is probably size and offset. But anyway, I want to say like start pointer. This is a pointer to U8. And then I'm gonna cast the pointer to pointer to U8. And then we have an end pointer, which is also a pointer to U8. So here I'm gonna cast, pointer to U8, and then I'm gonna plus the size. So that's the start and end. And we're gonna align the start address upwards and the end address downwards. So you're gonna say if start, thank you for following. We're gonna align with 8 bytes. That's the max alignment we have to do. So if start pointer and 7, plus 8, and we have to use this weird operator. And 7. There we go, that's gonna align it upwards. And then we track the end pointer. And 7. So now we're not increasing it by 8, so we're gonna align it downwards. So that's aligning the stop and start. Let's just print the pointers, so we know we're on the right track. Start pointer and end pointer. And let's call it down here. I'm gonna call allocator init with buffer. So this is an array and a pointer as well. And the size is 1024. What the hell? Is this gonna try to print? Is this gonna recursively print the pointers? I think it's actually printing what it's pointing to. Yeah. Tree printer. So this would have to be false. Sorry. Start is this. So it seems to just leave the values as it is. It's not gonna align anything, because it's probably aligned by default. If I did like 1023 instead, it's gonna align it. So we have 1F is aligning it to 18. So align the start and end address. And yeah. So now we have to insert the start block, which is this one, and an end block here. So we have to insert these blocks here. And this is going to point here, this is going to point there. So I'll probably just do split screen. That's probably the best. I'm gonna say start block. That's a pointer to block info. That is casting the start pointer to a pointer to block info. That's a start. And for the end pointer, I'm gonna cast the end pointer minus 16. So this is the size of the block info. So that's gonna first decrement this pointer to here, and then you assign it as a structure. So that's our blocks. Let's configure the end block first. So this next is equal to 0, and block size is equal to 0. Start block next is equal to start block next is equal to end block, and start block size is equal to that will be end pointer minus start pointer minus 16, which is the size of this guy. So that's configuring those blocks, and then we have the global allocator has a dummy block. So we're saying this next is equal to start block, and allocator dummy block size is equal to 0. So you're basically setting the properties of this one. So this is pointing to the first one and as size 0. And then we're gonna set the start and end. So allocator start is equal to start block, and allocator end block. There we go. So just configuring the settings here. It's setting up the structure so it looks like this, the top case here. So this is now pointing over here. So at the very end we can just try to iterate. I'm gonna have an iterator which is gonna infer the value of I'm gonna say like start block. I'm gonna say while iterator, why that's valid, print got a block. I'm gonna print the size. This will be iterator size. And iterator is equal to iterator next. So we should get one thing iterator next. Yeah, so it should get 3 blocks, I think. Search and type binary expression. What the 188 in typer. Binary minus. We're doing minus on a pointer. Thank you for following. So it's this. This should be end address. That's a pointer. Fuck. Let's use a U64 instead. We're still having start pointer. Oh, we're doing end. This is a failure. I don't know. Dang it. Oh my god! Zoning is rating with a party of 184. Thank you very much. Thank you so much. That was very nice of you. That's very nice. Yeah, so Zoning is doing some game development. This is really cool. So go check him out. Definitely worth the time. Like, what did you do on stream today? Was it fun? Yeah, that's a week. By the way, we're master's graduate students. Yeah, probably. Probably. No, not a virtual machine. I never did a virtual machine. I did the operating system though, but not the VM. Isn't alignment a bit wasteful? Yeah, but we're only aligning with 8. We're making sure that we can't really assign something not aligned to a pointer. That's going to generate some alignment fault or something. I was fighting with Windows C++ compilers. That sounds really fun. No. Oof. Hot reloadable configuration file. Oh, that's cool. Is it in like relation with the game? Relating to the game? Your language is self-hosting? No. This is just, we're trying to make an allocator. Yeah, so what we're trying to do, we're trying to make a memory allocator, a linked list allocator in the new language, just to see how well it performs. It's gonna see if it works. Yeah, that's the plan. So, and currently we're getting an error in the typer. We have a binary expression, which is like, I think it's this minus here, which doesn't really make sense. Oh, wait a second, is this one? So we're doing end pointer minus 16. No, that's still... So I'm thinking maybe this cast doesn't work. I'm actually gonna check in here the plus. I'm gonna generate an error on the plus instead. So here I'm gonna generate binary operator so you can see where it is. So it's in the end pointer, cannot use minus here. So this will be casted to, okay, it's doing end pointer. It says end block, cast block info. Let's see where that is. End block. Thank you for following. Thank you very much. Yes, reloading in-game contents. That's cool. Yeah, I think it's something funny with the pointer, like the casting. I'm gonna check it. So I think it's here we're assigning end block, which is a cast to, we're casting it to pointer block info. And then we're saying identifier is end pointer minus number. So this should work, assuming that end pointer is not a pointer. Identifier. So this is end pointer. We have it down here. It's a declaration. That's very, very weird. Oh. No, I'm just checking if it's minus. This is gonna happen all the time if I'm doing minus. So I'm gonna check if any of the sides is a pointer. So basically if pointer left or is pointer right. The reason is just we haven't implemented it. So everything with pointers and minus is not going to be allowed at the moment. And this is very cool. So we're getting 2 blocks. This is so cool. We got a block which has a size 1000 and we got a block which has a size 0. So why don't we get the first one? Yeah, that's correct. So we're actually setting it to the start block. So I guess the start block is wrong. So the allocator start is the start block. This is really going to be the address of allocator dummy block, right? The start should be this block here, which is the dummy block. So now we should have I'm setting it to start block. Let's do allocator start instead. So now we're getting 3 regions, 0, 1000, and 0. So pointers are, to be honest, I don't know how this works. What the hell? That's so cool. Alright, so let's, this is the init, and it sets up the allocator correctly. Yeah. Alright. So what we're trying to do, we're trying to make some kind of allocator which looks like this. Gonna make it a little bit smaller. Might be easier to see. I'm gonna actually use this case here. So we're gonna make one function now which is very simple. And it is gonna do one single thing. This is not really how it looks. It's gonna do one simple thing. It is gonna insert, I'm guessing gonna support multiple regions. So I want to track the ending node and the start node. So this is gonna be called start, and this is gonna be called end. So I want to insert a node between start and end. It's going to take in insert something. And this might be this node here. So I want to insert this node into the free list. So basically I want this block here to be free. I want this to happen. So then I need to, first of all, make sure the links are working, and then I need to check if I can overlap these blocks. Thank you for following. So what I'm gonna do, I'm gonna insert this one. I'm gonna check if the previous one is overlapping with the inserting one. If that is the case, I'm gonna extend this block over here. I'm gonna increase the size, and I'm gonna set the insert block down here again. So basically the case is still the same. I want to check if the insert block maps or overlaps with the next block. And finally, if the block to insert is not equal to this block here, basically this doesn't overlap, then I need to make sure this is pointing here. Something like that. So I think I'm actually going to take that on the side because it's kind of tricky. Thank you, Raddy, for following. Welcome to the stream. Welcome, welcome. We're going to make an allocate. Yeah. So this is going to be a function which takes in a size U32. Let's do U64. And we're gonna make a free. So the free function is gonna take in a pointer, while the allocate is gonna return a pointer. It's gonna return a question mark pointer, so a weak pointer. So this has to be checked before it can be used. So let's just return 0 and see if it works. So I have some kind of pointer. I don't know, because I'm not with equal sign. I'm a little bit unsure how that's gonna go. Let's just return a strong pointer for now. So any pointer will do. And then I'm doing pointer. I think inferred should work. So allocate size 45. Oh, free is a GCC thing. Let's do delete instead. Okay, it works. Yeah, so both the allocate and delete is gonna call this function, which is gonna insert into the free list. Hello, Rowdy from Brazil. Hello, hello. So I'm gonna make insert block. So it's gonna take in three things. It's gonna take in the first block, last block. No, I'm just gonna specify the block I'm gonna insert. So this is a pointer to block info. So I'm gonna insert this block here. So the one thing I have to do first, I have to iterate this list so that I know the pointer here and the pointer here. So I need to like have a double iterator, and I have to iterate as long as this pointer is smaller than this address here. So I'm gonna start with the after. I'm gonna call this after, this before. So after is gonna start here, before is gonna start here. So I'm gonna have two iterators. After is a pointer to block info, which is equal to allocator start next. Yeah, and before. Thank you for following. It's also a block info, which is going to be allocator start. It is very convenient to just ignore the pointer thing and just write that. It's very cool. And then we're going to iterate as long as after is something, and that after is bigger. We have to use the address. So I'm going to say cast after to U64. Well, that is smaller than insert U64. So while after is something, and while I think that's just, I don't know if I need a caster. Probably not. But while the after block is smaller. So while it's, yeah, okay. So while it's smaller. So while that is happening, we're gonna say before is equal to after, and after is equal to after next. So it's gonna do the double iteration. And then we have to check if after is equal to 0, return 0. So this should probably be, this should be a failure. Yeah, this is like an insertion fault, because the last block will eventually be this one, which is at the very end. So if it doesn't, yeah, that's like out of range. So this will not happen. We can just print an error. What all do I need to know to build a compiler? It's a good question. You need to know recursion, and you need to know, like, you need to know how a language works pretty well, like how pointers work. So C is a good start. I feel by learning C, you know this kind of thing. I don't know, but you have to know like what pointers is, what how they work, how they're implemented, and you need to know a little bit about what structures you should be using. Because I'm using like a lot of structures, and by knowing like some of these, what they're supposed to look like how to parse expressions, how scopes work, how you should add stuff to the scope, how declarations are completely different than statements or expressions, like stuff like that helps. It helps a lot. Yeah. Plenty of patience. Memory manager. How was the first compiler made? I guess in assembly. You shouldn't learn anything from Yarn. Freeing will be very slow. That's correct. It will be, but you have to track the address as well. You need to know where to put it. Like, I mean, you can't just use a free list. It really depends. What's an assembler? Yeah. Start with C. That's a good start. All right. So this is an error. So I'm just gonna return. I don't think I can return. I cannot call exit either. Well, this is not gonna happen. I will probably have an assert later. We can, like, I think we can call assert. No, we can't. Anyway, so now we should have the after and the insert block. So now we need to check overlapping. So I need to check if the before block cats before, if this one plus the before size, if that is equal to the insert address. So basically, if this one plus the size is equal to the next one, if they can be combined. So now we're gonna merge these together. You just say before size is equal to before size plus insert size. So increasing the size of this, and you say insert is equal to before. And this is really nice because now we can, you don't need to track like two cases, it's always one single case you have to track. And now we need to check if don't need those. If cast insert to U64, and remember this might either be this block here or this block, depending on if it's combined. Plus insert size, if that is equal to after so if that's equal to after, then everything can be combined, assuming the block after is not the end. So I have to check if after equal allocator end. Yeah, allocator end. If after is equal to allocator end, then we cannot combine them. They cannot be combined, and the pointer next should point to the last one. Cannot after merge. I don't know, insert next is equal to after. Otherwise, okay. Otherwise, insert size is equal to insert size plus after size. And insert next is equal to whatever after is pointing to. So that will be like after next. So that's the case where they can be combined. So what if they cannot be combined? Then this will be pointing here. So we have else insert next is equal to after. So we can see this is also happening here. So I'm gonna instead do if they're not equal. So if they're not equal, you're gonna merge them together. Otherwise, you just make the link. So now let's recap. We have combined these blocks here if possible, and we also combine this if possible, and in any case we fix this link. And if this is merged, we don't need to fix this link. If this is not merged, so if insert is different from before, if insert is different from before, then you make the link before is equal to insert. I'm not going to track this. So that's about it, I think. Yeah, that's it. Let's see if it compiles. No, it doesn't compile. Oh, I'm using the wrong name. Allocator. It's supposed to be an O instead of an E. Variable is not declared. I think I have a typo there. Allocator. There we go. So it's compiling at least, which is very good. Okay. So let's implement the allocate. So if size is equal to 0, just return 0. So that's why this should be a weak pointer. And then we need to do size is equal to size plus 16. We're gonna add space for the info block, and then we're gonna align it. So if size and 7, then we do size is equal to size plus 8. I don't have that operator. I have to copy the operator. That's going to be very annoying. I have to change it. And 7. So now the size is aligned. Allocating. Thank you for following. Okay, so that's allocation. So now we have to iterate. I'm gonna do a double iteration again. I'm gonna basically iterate here and stop when I find a block which is big enough. And I need to keep the previous pointer because I'm gonna unlink it. So I'm gonna do the same thing as here. So allocator start next. And yeah, you just do this. So now we're gonna iterate as long as after size is less than size. So as long as the block has a too small size, it's gonna keep iterating. And if after is equal to 0, basically out of memory. So now we have an after block which is big enough to contain the size. So we're gonna first unlink the block. So we're saying that before it's equal to after next. We're basically unlinking it. So this is now going to point wherever this is pointing. So this doesn't exist in the list anymore. And we're going to return this to the user. We're going to return the after pointer plus like 16 bytes. We're going to give the user this pointer instead of this. So now we need to check if the remaining part can hold a new block. So if after size minus size so if after size minus size is, I'm gonna say like, is bigger than 16, which is the size of the block. The remainder can hold a new block. So let's see if we can find an example on this. We're trying to allocate this little block here. So we know that this remaining part can hold a new allocation. So I'm gonna insert a new block here after this. So I'm gonna take this pointer plus the size, and that's gonna give me the pointer to the next one. I'm gonna have a new, which is also a block info pointer, and that'll be, we're gonna cast to pointer to block info. And then we cast after to U64 and we plus with a size. So this is getting the address of after. No, yeah, address of after, that's this one. You plus it with size, that's gonna give you this one. and you cast the block info, that's going to give me this block here. And you need to set new size, which is equal to after size minus size, and new next. You don't really track the new next, you're just going to insert it. So here we have like insert block, we're going to insert new. Is that correct? Thank you for following. So we're setting the new size, we probably have to update the previous size as well. So say before size is equal to just size. So now we're updating the size of the previous one, and you just return a pointer, I guess. So that's the no, this is after size. You're only using the before to unlink the block. So return cast after to U64, and we're going to cast that to a plus 16 to any pointer. All right, is that correct? Before next, well, it seems right to me. Let's have a loop. So while one, I'm gonna allocate something new. So allocate 45, and if new 0, I don't have break, so I'm gonna return print out of memory. If that is not happening, we're going to print new pointer. We're going to print the address like that. Expecting. What the hell is it expecting the line here? I don't know. Like that's. I don't know why that happened. That's weird. It should be plus. Look at member instruct. So this is something internal to the compiler. It is looking up some kind of member in something which is not a struct. Thank you for following. That's in typer 302. Typer. So we're asserting that this is a structure. And we're getting a name. Where am I calling that? I'm calling it here. So if the dot expression type dot token. I want to see where this happens. So it's happening here. So new size. So basically new is not a structure. And why the hell is new not a structure? This is a block info. It says type. It's typed. I think it's also just type. New. Where is new? Where is that function I'm looking for? Thank you for following. That's allocator init. This is the allocate. And we have declaration after and before. That's the only one, which is really wrong. We have more. We have this new one as well. So it doesn't seem to go into like if statements. So if I would declare this outside, I think it should work. We can track that first. Thank you for following. I just use new is equal to something. So I have segfault, that's perfect. I think the init should work. Done iterating. It isn't done iterating, so probably the failure happens here. Nope. It's not even up there. It's allocating, and it gets different pointers. What the hell? If I was printing something, it worked. Segmentation. That doesn't make any sense. Now it works if I just print stuff. And out of memory at the very end. So that is interesting. Very interesting. Why do you need gaps? I don't need gaps. I try to avoid the gaps. That's why I'm trying to merge them together. Or what did you mean, really? Oh, the gaps, yeah, they're info blocks. It's telling the size of it, and it holds the pointers to the next one. Is new a reserved keyword? It is gonna be, because I don't like to do I don't like to do size of, for example, this. I just want to do, yeah, I don't know what the syntax is gonna be, like s, we can use this as well, new, or we can say what it's gonna be. I don't know, it's gonna be like the new keyword. I don't wanna write this. But also, this only applies to like the internal allocator. If you want to have like custom allocators, you still have the same syntax. So maybe you can do some kind of cool compiler thing to make this syntax here available. Like make custom keywords. Like type defing-ish. I don't know. 2 seconds, let me just check something. I need a different keyboard. I'm gonna write in Norwegian. So stupid. All right. There we go. So I'm getting a little bit more time. So we're just gonna continue. We're gonna make this work. So we have a seg fault without iterating. That is really stupid because I want to iterate. I want to print to see where the seg fault is. If I print here, now it's working. It's working if I print. Oh my god. That doesn't make any sense. So we have a seg fault if it doesn't print. So maybe the memory is corrupt. It has a seg fault. What's the code look like? Oh my god, 600 lines for that simple stupid allocator. Oh my gosh. We're allocating the buffer and we're allocating the allocator, which is 8 bytes. Okay, that should be correct. Something tells me this is wrong. Assigning stack. So we're gonna have allocator where is buffer? No, not the buffer. Yeah, so new is assigned. It's assigning everything. Let's try to return. Okay, so that this actually succeeds. It's the allocate which is wrong. So let me try one allocation. That's a segmentation fault. Okay, so I'm gonna still have the return now. I'm gonna try to return from the insert block. It's very weird. So I have a seg fault there. It seems like there's a seg fault when actually calling this. Oh, this is insert block. That's not the problem. It's in the allocator. So we're not printing allocating you. If I return, I think maybe the print is wrong. I hope not. The print is wrong. The print is messing up. Why? Emoji. You can give alloc the type you allocate. Yes, probably. But it's a allocator. Who cares if it's 700 lines? Yeah. I really don't care. Especially with x86, I don't care at all. 5.5k lines, alright. That's definitely more. Like, we can print in here. We can print in here. If I do size in there, I think it worked. And now that works as well. So yeah, something is very wrong with the print stuff. It's very hard to debug this. Yeah, inferring. I'm inferring stuff down here. So I'm saying that new is supposed to have the type of allocate, and it doesn't find it. Actually, the inference is working pretty well here. That's kind of cool. Is that supposed to be a LD? It is the allocate which fails. So the function size 32. Okay, still the segfaults. So if I'm calling allocate up here, it's still a segfault. It's depending on maybe it's because I'm inferring or something. Oh, new variable is not declared. I'm just gonna say this is a pointer. Okay, so it's because I'm inferring. Let's try to do just a new equal. Makefile, segmentation faults. Okay, let's go in the generator. I'm generating the assign expression here. So we're first generating the left-hand side. Pushing here, isn't that wrong? Like generally, you want to compute the right-hand side first. If you have like equal equal. You want to take this first, and then you want to compute this one. So Rax is the left-hand side. I'm taking the binary right first and then the left. I'm popping into RDI. Let's think here. There is something funny in here. Standard x64. Yeah, it's using standard x64. Everything is past its U64. I guess something is corrupting the stack. And if I'm doing the left first, it's gonna push the address. And then you do this. Generate the expression right. And the left is the address. It's weird. Let's see what, where that happens. Thank you for following. This is happening here. And new is allocated on stack. So I get as this is the new one. I should probably print the offset as well. Width size something and minus offset. Oh, we're getting nothing. There we go. So new should be at -8. So we're loading this into memory, into RAX. We're pushing RAX. So this here is the load variable. And then we're moving 35, so that's the argument. So we're pushing RAX. So this is argument. And then we're popping RDI. This is popping the arguments. And then we're moving 0 to racks, which is correct. And then we call allocate. So after call allocate, we're popping oh. Okay, so here's the problem. This is the allocator, and then we're popping RDI. Yeah, pop RDI. So that is correct. But it's also very weird that if I print something, it works. Because the code is literally doing the same thing, I think. It's calling to printf first. And loading arguments, popping arguments. Moving 0, call allocate. It's literally doing the same thing. I don't understand why. I should probably have a debugger. It's very weird. My brain has stopped now. Anyway, let's just print something then. Yeah. So like this. All right. Let's not return 0. Segmentation fault even with the print. You totally should have a VM for the ASM you're outputting. Yes, I should. I probably want to fix that first, because this is quite annoying. And it doesn't get any simpler when this compiler is getting more complicated. So I probably should fix that very quickly. I'm not using Vim, I'm using Vim. I'm not using anything for VS Code. Yeah, I can use GDB. I can set it up. Yes, I can. Dang it. I don't understand, even when the printing it doesn't work. Oh. It's allocating stuff. And I should probably have a random function as well, and that probably will require floating points. So I can't really test this to see if it actually works. I can allocate a pointer, and I can print it, and I can free it again. I don't have delete yet. So delete, that will be that is just a pointer. So you say new block. We can infer here. So that's going to cast to a pointer to block info, and we say pointer to U64 minus 16. So we're basically getting this info block. And then we're gonna just insert this block into the free list. Yeah. Insert block new. Block memory. Does it really quit here? Should allocate it and just free it as well. Delete block. I'm not deleting it. I thought I did. Delete new. And it just goes. So it's basically returned the same pointer, so it allocates and frees it directly after. So it is working, like the implementation is working, I think. We can also try to allocate a little bit before this, just to check that the list is implemented correctly. And let's say data is equal to this. You allocate. And then you delete data. So that should have some gaps in memory. And it still works. So that's very cool. It just sucks that print error. If I delete the print, it doesn't work. But I'm gonna get JDB up and going first. Oh, now it works. What the fuck? Oh, it's because I'm not assigning it. I have to call a function first, so maybe this is corrupting something. It's very hard to say. Yeah, anyway, but at least this is beginning to work. We can actually write real-world programs in this language now, which is really cool. So we did casting, we did bit operations, logical and... Yeah, it's beginning to look very good. I think I want to clean it up though. I have to go through. So the next... I also probably want to write some kind of list where I like plan what I'm gonna implement next. I guess an interpreter is gonna be nice, because then I can start writing in multiple files. I can have one single file for syscalls. Yeah, so the syscall, where is the syscall again? I have it on the GitHub. I don't know why I deleted it. Let's see, it's in the test folder. There we go. Thank you for following. So I would like one single file with just the syscalls. So that's going to be like a standard library. Yeah, something like that. And also, yeah, I'm gonna commit this. Added cast and yeah, probably just this. Can't remember everything we added. Okay. And it's also very nice that I don't need to consider the order. So here I'm accessing allocator. That's defined down here. You say like allocator or something. And that's also, I think this is very cool. So if I like, in here I can say print data, and I'm gonna print the variable square. I'm gonna print this variable, and I'm gonna say like square is equal to 234, and I can define it down here. Square is a U64, which is equal to this. This is allowed. This is totally fine, which is really cool. So you can actually paste in code very, very easily. Doesn't matter the order. Everything you can place everywhere. Doesn't matter. All right, I'm gonna delete what we did here. I've committed it, so we're gonna take a look at it the next time. So I'm not sure. Also, the next time I want to implement the print function. Because ideally we should have everything in this language. So currently to print something other than like strings, we have to call printf. which really sucks. So we have to implement our own prints. But that would require like variable argument list. And I don't know how we're gonna implement that. It is very simple, but we have to find something which is better than C because I don't like it. Not any VI list or any crap like that. Yeah, but I think I'm gonna quit for today. I don't know how long I've been streaming for. 5 hours? 3-4 hours? 6 hours, okay. Extra noises. Yeah, 6. Didn't work. Yeah, so I think I'm just gonna quit now. And I'm gonna clean up the code. I usually do that best alone. Yeah, sounds good, but we have implemented like a lot of stuff here. So it's beginning to look like a real compiler. So it's very cool. Nice stream, thank you. Got the generator and interpreter to work with all basic arithmetic. That's very nice, congratulations. That's very cool. I'm also gonna look at the interpreter. I've never done an interpreter before, which is really embarrassing to say. Or I guess it isn't, but I'm gonna take a look at it soon. Let's find somebody to raid, shall we? Learning Go. Game dev and advanced C++. Maybe we're lucky today and find someone who streams C. Nobody's streaming C, it seems like. Developing chess, Scala. I think that's a language. I think I heard of it. I'm literally looking for C or C++. Linux USB. Looking. Not a fan of Scala. I've never tried it. I know it's a language. Let's rate C++. Advanced game development. That seems cool. Somewhat accurate. Yeah, so I'm gonna rate him. It is starting to get close to my exams, so I don't know. But I probably will stream in like tomorrow or in 2 days. Anyway, yeah, have a nice day, and I see you next time.